Hello, you are already exactly where you need to be, lying in the dark, letting the day soften and fade behind you. There is nothing to solve right now, nothing to fix, no test at the end of this. Just a quiet voice, keeping you company for a little while as you drift towards sleep. You don't have to pay close attention. You don't have to follow every detail. If your mind wanders, that is perfectly fine. That is what it is supposed to do. This is just a quiet story about something strange and real, something that lives in the smallest corners of the world. And if you miss a piece of it, the words will keep flowing, soft and steady, and nothing will be lost. Tonight we are going to talk about a connection between tiny particles, pieces of the world so small you cannot see them, cannot feel them, cannot hold them in your hand. These particles can become linked in a way that is hard to describe with everyday words. Once they are linked, whatever happens to one of them seems to be reflected in the other, instantly, no matter how far apart they are. One could be here, on this planet, and the other could be drifting out in the quiet dark between the stars, and still, somehow, they would remain connected. This is not a metaphor. This is not a poem. This is something physicists have measured and tested and confirmed, over and over, for decades. And yet, when you sit with it, when you let the thought of it settle in, it feels like a kind of quiet mystery, a mystery we can rest inside tonight. The first thing to know is that you are allowed to find this strange, more than allowed. Even the people who study this for their whole lives, the physicists who work with the equations every day, even they will tell you that it sits uneasily in the mind. It does not fit with the way we usually think about the world. In our ordinary life, things that are far apart are separate. A stone on a beach in one country does not feel the waves on a shore across the ocean. A leaf falling from a tree in a forest does not make another leaf tremble in a city miles away. The world we walk through every day is a world of separate things, each in its own place, affecting each other only by touch or sound or light or some other force that travels across the space between them. That is the common sense we are all born into, and it works. It works for doors and chairs and cups of tea. It works for planets and stars. But it turns out, deep down, at the very bottom of things, the universe is not put together that way. Down in the realm of the unimaginably small, separateness is not as solid as it seems, and that is what we are going to wander through tonight. Slowly, calmly, without hurry. I promise you plain language. I promise a slow pace. There will be no equations, nothing to write down, nothing to remember. I will not use numbers that look like symbols on a page. Every number will be spoken out in full, like 1935. So your mind does not have to picture anything sharp or precise. The words will be simple, the kind of words you might use to describe the weather, or the color of the sea, or the feeling of a warm blanket. Because the ideas themselves are enough. They don't need to be dressed up in complicated language to be wonderful. In fact, the simpler the words, the closer you get to the quiet heart of the thing. We are going to start very far back, with a look at the world of the very small, because to understand this strange connection, this link between particles, you first need a sense of the tiny stage on which it happens. We will talk about atoms, and the even smaller pieces that make up atoms. We will talk about electrons, which are little specks of matter, and photons, which are little packets of light. And we will talk about how, at that tiny scale, the rules change. Particles do not behave like marbles. They do not behave like baseballs. They seem to be able to do something that sounds impossible in our big, solid world. They seem to be able to be in more than one state at the same time. They hold multiple possibilities at once, like a coin that is somehow both heads and tails until the moment you look. This is called superposition, and we will spend time with that idea, because it is the doorway. Once you understand superposition, even just a little, the idea of entanglement begins to make a kind of sense. Not the sense of everyday logic, but a deeper sense, a kind of quiet acceptance that the universe might be built differently than we assumed. And from there, we will step into entanglement itself. What it actually is, how it was first described. We will meet some of the people who discovered it, who argued about it, who lay awake at night thinking about it, just as you might be lying awake now. One of those people was Albert Einstein. He found the whole idea deeply troubling. He called it something like spooky action at a distance, and he meant that as a complaint, as a way of saying that something must be missing from the picture. He spent years trying to find a way around it, a way to explain the results without this strange, invisible link stretching across space. We will talk about that. We will talk about a paper he wrote in 1935 with two other physicists, and we will talk about how that paper, which was meant to show that quantum mechanics was incomplete, actually helped open the door to a deeper understanding. The not knowing was there from the very beginning. It is part of the story. Then we will meet a physicist named John Stuart Bell, who in the 1960s found a way to turn the whole philosophical debate into a question that could be tested in a laboratory. He found a way to ask nature herself whether these hidden connections were real, or whether there was some simpler explanation, some set of hidden instructions carried by the particles from the moment they were created. And we will follow that question into the laboratory, where real experiments were done, with photons, with detectors, with careful measurements repeated thousands and thousands of times. The results were clear. They said something profound about the structure of reality, and those experiments were so important that the physicists who led them shared a Nobel Prize, not in some distant future, but just a few years ago, in 2022. This is not ancient history. This is settled, tested, confirmed science, and yet it still sits strangely in the mind. It still feels like a door that opens onto a room we do not fully know how to furnish. We will also be careful, as we go, to say what entanglement does not mean. There are many ideas floating around in popular culture, ideas that this strange connection could be used to send messages faster than light, to communicate instantly across vast distances. That is a beautiful idea, but it is not what the physics says. We will talk about why. We will talk about the difference between correlation and communication, and why, even though the two particles seem to know about each other instantly, you cannot use that link to send a signal. The speed limit of light, built into the structure of space and time, remains unbroken. The universe is strange, but it is not lawless. Its strangeness follows rules, and those rules are consistent, and we can rest in that consistency even when the results surprise us. And after we have said what entanglement does not mean, we will sit for a while with what it might mean. Because this is where the real calm lives. This is where the not knowing opens up. Physicists still debate what entanglement tells us about the nature of reality itself. There are different ways of interpreting the same set of experimental results. Some physicists think that the act of measurement brings reality into being, that the particle was truly not in one definite state until it was observed. Others think that every possible outcome actually happens, but in different branches of reality, splitting off from each other like paths in a forest. Still others think that there are hidden guides, invisible waves that pilot the particles along definite paths, paths we simply cannot see directly. None of these interpretations has been proven right or wrong. They all explain the data equally well, and so the physics community lives with this open question. They hold it gently. They do not need to solve it tonight, and neither do we. We can simply let it rest there, a question mark at the heart of things, and find that resting place deeply peaceful. Then, toward the end, we will look at where entanglement is used. This is not just a philosophical puzzle. It is also a tool. Real technologies are being built on the back of this strange connection. Quantum cryptography uses entangled particles to create codes that cannot be intercepted without leaving a trace. Quantum teleportation uses entanglement to transfer the exact state of one particle to another, far away, without moving any matter through the space between. Quantum computers use superposition and entanglement together to work on certain problems in ways that ordinary computers never could. These are real machines, working in laboratories around the world. They are not magic. They are engineering, built on decades of settled science, and yet they trace their lineage back to those quiet, unsettling questions that Einstein and others asked almost a century ago. And finally, we will widen the lens. We will step back from the details and look at the bigger picture. We will reflect on what it means that the universe, at its smallest scale, is not a collection of separate little marbles, but something more like a web, a fabric, a single interconnected whole. We will sit with the thought that separateness might be something of an illusion, a useful approximation for our big, slow world, but not the deepest truth of how things are. And we will do this calmly, without urgency, without the need to pin anything down, because some mysteries are not meant to be solved and put away. Some mysteries are meant to be lived with. They are companions in the dark. They keep the mind company without demanding answers. And that is the spirit in which we will close, not with a summary of what we have learned, not with a call to action, just with a quiet image to hold as you slip away. Two particles linked since their creation, still connected across whatever distance has grown between them. A quiet reminder that connection is woven into the fabric of things, and then stillness, and then sleep. So that is where we are going, but we are going there slowly. Very slowly. There is no rush. The words will come at their own pace. The sentences will stretch out and breathe. There will be pauses implied by the rhythm, spaces where your mind can rest. If you find yourself drifting away from the thread of the story, do not pull yourself back. Let yourself drift. The thread will still be here when you return, or it won't, and either way is fine. This is not a lecture you need to follow. It is more like a landscape you are passing through. You can look at whatever you like. You can close your eyes and just listen to the sound of the words without holding on to their meaning. The sound alone is enough. A low, steady voice, speaking about things so small and so vast that they put the day's worries in a different perspective, or simply let them fade into the background hum. The strange connection we are going to explore is, in its own way, a very old idea, dressed up in the language of modern physics. Poets and mystics have long suspected that the world is more deeply connected than it appears, that everything touches everything else in some hidden way. What physics has found is both more precise and more limited than that poetic vision. It applies to specific particles under specific conditions. It is not a general rule that everything is entangled with everything else, and yet it shows that the possibility of deep connection is built into the fundamental laws. The universe allows it. The universe, at its foundations, does not insist on strict separateness. That is a fact, not a metaphor. And it is a fact you can hold in your mind like a smooth stone, turning it over slowly, feeling its weight, its texture, its quiet strangeness. Take a moment, if you like, to settle deeper into wherever you are lying. Feel the weight of your body on the bed, the pillow under your head, the blanket over you. Notice that you are a collection of particles, trillions and trillions of them, arranged in a particular pattern that is you. And those particles themselves are made of smaller particles, and those smaller particles obey the strange rules we are going to talk about. So in a way, you are already a citizen of this strange quantum world. You are already part of the story. You don't need to do anything to earn your place in it. You are in it by the simple fact of being made of atoms. The strangeness we are going to explore is not something happening far away, in a laboratory you will never visit. It is happening in every cell of your body, right now, underneath the level of your everyday awareness. The solidity you feel, the separateness you feel, is a kind of surface effect, a useful smoothing out of a deeper reality that is much more fluid and interconnected. And that thought, that gentle unsettling of the usual categories, can be a very comfortable thing to fall asleep to. It softens the hard edges, it blurs the boundaries between you and not you, between here and there, between now and then. So let us begin, not with a bang, but with a slow unfolding. Let us start where all good journeys start, with a look at the ground beneath our feet. Or rather, since our feet are too big, with a look at the ground far beneath our feet, the ground of atoms and electrons and photons, the world of the very small. We will go there next. We will shrink down, in our imaginations, past the level of dust motes and cells, past the level of molecules, down to the individual atoms, and then inside the atoms themselves, to meet the particles that live there. We will learn their names and their ways. We will learn that they are not like little balls of matter. They are more like little knots of possibility, little clouds of maybe, held in a dance that has been going on since the beginning of time. And all of this will be described in the calmest, plainest language I can find, words you already know, sentences that flow like a slow river. For now, just breathe. Let the day go. Whatever happened today, whatever joys or sorrows or frustrations or small kindnesses, they are all behind you now. They are part of the past. Right now, in this moment, there is nothing you need to do. There is just a voice in the dark, talking about tiny things and vast ideas, keeping you company on the edge of sleep. You are safe, you are comfortable, you are exactly where you need to be, and the story is just beginning, very softly, very slowly, like the first faint light of dawn, except we are moving the other way, into the quiet dark, into the world of dreams. Close your eyes if you haven't already. Let the words wash over you. Let the meaning come and go as it pleases. You are not being tested. You are not being graded. You are just being given something to rest your mind on, a gentle focus that asks nothing in return. And in a moment we will step into the world of the very small and see what lives there. So let us step into that world now, the world of the very small. Let your imagination drift downward, away from the room you are in, away from the bed and the pillow and the blanket, away from the scale of things you can see and touch. Shrink down in your mind past the dust motes floating in the air, past the tiny cracks in the ceiling, past the threads of the fabric beneath your hand. Keep going, smaller and smaller, until the familiar shapes dissolve into something else entirely. This is where our story lives. Not in the world of tables and chairs and cups of tea, but in the hidden landscape underneath all of that, the landscape that makes up everything you have ever known, everything you can see, everything you can touch, everything you can taste or smell or feel the weight of. All of it is made of atoms. The pillow under your head, the air moving in and out of your lungs, the cells of your own body, the skin and bone and blood, all of it, built from atoms. Atoms are the tiny building blocks of matter. They are so small that a single grain of sand contains more atoms than there are stars in the entire Milky Way galaxy. Let that settle in for a moment. A single grain of sand, something so small you might not notice it on your palm, contains more atoms than all the stars you can see on the clearest night, and all the stars beyond those, stretching out across 100,000 light-years of space. That is how small an atom is. It is a scale that the human mind was not built to picture directly. We can say the numbers, we can write them down, but truly imagining that smallness is like trying to imagine the size of the ocean by looking at a single drop of water. It is a useful stretch for the mind, a gentle loosening of the usual categories. Atoms themselves are not the smallest things. They are not the end of the road. Each atom is made of even smaller pieces. At the center of an atom sits a tiny, dense core called the nucleus. Around that nucleus, arranged in layers like the skins of an onion, orbit the electrons. Electrons are tiny particles of matter, unimaginably light, moving around the nucleus at incredible speeds. They are not like little planets orbiting a sun, not really, but the image of a solar system in miniature was how many people first learned to picture an atom, and it is a gentle place to start. Just hold it loosely. Do not grip it too tightly. It is a stepping stone, not the final picture. And then there is light. Light, which seems so smooth and continuous when it washes through a window, is also made of tiny individual pieces. These pieces are called photons. A photon is a single particle of light. When you turn on a lamp, trillions and trillions of photons stream out into the room, bouncing off the walls and the furniture and your skin, and some of them enter your eyes, and that is how you see. Light is a rain of tiny particles, each one so small and so light that they have no mass at all. They are pure energy, pure motion, crossing the room in a fraction of a second. These three things, electrons, photons, and the nucleus at the heart of the atom, are the main characters in our story. There are other particles too, with other names, but we will not need them tonight. Electrons and photons are enough. They are the ones that show us the strangeness most clearly. They are the ones that become entangled. They are the ones that do not behave like marbles or baseballs. And that is the central fact we need to sit with now. At this tiny scale, particles do not behave like the objects we are used to. A marble is a solid little sphere. You can hold it in your hand. You can know exactly where it is. You can roll it across the floor and predict exactly where it will end up, because the rules of motion for marbles are rules we all learn as children. You push something, it moves. You let it go, it stops. Things have definite places. Things have definite speeds. A thing is here and not there. That is the common sense of the big world, the world of tables and chairs. And it works perfectly well for tables and chairs. It works perfectly well for marbles and baseballs and planets and stars. But when you go down to the scale of electrons and photons, that common sense begins to fray. It does not break. It does not disappear. It just becomes something softer, something less definite, something more like a suggestion than a rule. This field of study, the study of how matter and light behave at the very smallest scales, is called quantum physics, or sometimes quantum mechanics. The word quantum comes from a Latin word meaning how much, and it refers to the fact that at this tiny scale, things come in discrete little packets, little chunks. Energy is not a smooth flow. It comes in small, indivisible units. Light is not a continuous wave. It comes in photons. The steps of the world at the bottom are grainy, not smooth. That is what the word quantum points to. But for our purposes tonight, we can think of quantum physics simply as the physics of the very small. The rules that govern the tiny building blocks from which everything else is made. And these rules are strange. They are strange in ways that even the physicists who discovered them found hard to accept. They are strange in ways that are still not fully understood, almost a century later. But they are also, and this is important, some of the most thoroughly tested rules in all of science. Quantum physics is not a fringe idea. It is not a speculation, it is not a guess. It is a set of mathematical descriptions that have been checked and rechecked, tested and retested in thousands of experiments over many decades, and they have never been found to be wrong. The predictions quantum physics makes are astonishingly precise. They match what we actually see in the laboratory to an almost unbelievable degree of accuracy. The theory works. It describes the world as it is. The strangeness is not a sign that the theory is broken. The strangeness is a sign that the world itself, at its foundations, is not built the way our everyday intuition expects. That is a thought worth resting on for a moment. Our intuition, our gut sense of how things should behave, was built by evolution to help us survive in a world of medium-sized objects moving at medium speeds. It was not built to understand the very small or the very fast. There is no reason it should work down at the level of electrons, and in fact, it does not, and that is fine. That is not a crisis. It is just a fact about the limits of our built-in mental tools. We can extend those tools with mathematics and with careful experiments. We can learn to think in new ways, but we should not be surprised when our gut says, that cannot be right. The gut was trained on apples falling from trees, not on electrons orbiting a nucleus. The gut can be a helpful guide, but it is not the final authority. And letting go of the need for things to make intuitive sense is one of the quiet pleasures of learning about quantum physics. It is a kind of mental exhale, a loosening of the grip. So what does an electron actually do, down at that tiny scale? What does a photon actually do? The first thing to understand is that they are not little balls. They are not tiny marbles. An electron is not a miniature version of a baseball. It is a different kind of thing entirely. It has some properties that we associate with particles, like a definite mass and a definite electric charge. But it also has properties that we associate with waves, like the ability to spread out and interfere with itself, creating patterns of peaks and troughs. This is sometimes called wave-particle duality, the idea that a quantum object can behave like a wave in some situations and like a particle in others. But a more accurate way to say it, or at least a calmer way, is simply that an electron is an electron. It is its own kind of thing. It does not have to fit neatly into our pre-existing categories of particle or wave. Those categories were built for the big world. Down here, at the quantum scale, things are more fluid. They are more flexible. They follow rules that are precise but unfamiliar. One of the most important of those rules is that you cannot know everything about a quantum particle at once. This is not a limitation of our measuring devices. It is not that we need better microscopes. It seems to be built into the fabric of reality itself. If you try to pin down exactly where an electron is, you lose information about how fast it is moving. If you try to measure exactly how fast it is moving, you lose information about where it is. The more you know about one property, the less you can know about the other. This is called the uncertainty principle, and it was discovered by a physicist named Werner Heisenberg in the 1920s. It is not a fuzzy edge of the theory, it is a sharp mathematical rule, and it tells us that at the quantum level, certainty has a limit. There is a horizon beyond which we cannot see, not because our instruments are crude, but because the information is simply not there. The particle itself does not have a perfectly definite position and a perfectly definite speed at the same time. It lives in a kind of blended state, a cloud of possibilities. That cloud of possibilities is the key to everything that follows. It is the door we will walk through in the next part of our journey. The idea that a particle can be in more than one state at the same time is so central, so essential to the whole story, that we are going to spend an entire section on it. It deserves its own space. For now, just let the image settle in your mind. A tiny electron, not as a little dot spinning in a circle, but as a kind of haze, a mist of maybe. It is not definitely here. It is not definitely there. It is spread out across a range of possible locations, and only when you go looking for it, only when you set up a measurement, does it seem to pick one of those locations and become definite. What it is doing before you look, whether it even makes sense to ask what it is doing before you look, is a question that physicists have debated for a very long time. And that debate is not settled. The not knowing remains, and we will sit with that not knowing calmly in the sections ahead. For now, we are still just setting the stage. We are still just looking around this tiny landscape, getting our bearings. We have learned that everything is made of atoms. We have learned that atoms are made of electrons and a nucleus. We have learned that light is made of photons. We have learned that at this tiny scale, particles do not behave like marbles. They are more fluid, more uncertain, more like clouds of possibility than like solid points. And we have learned that the field of study that describes all of this is called quantum physics, the physics of the very small. It is well tested, it is not a fringe idea. It is one of the most successful scientific theories ever developed, and yet it contains mysteries that are still unresolved. That combination of precision and mystery is what makes it such a restful thing to think about. The precision gives you something solid to hold on to. The mystery gives you something soft to drift into. Imagine, if you like, a single atom resting in the darkness. It is so small that 1,000,000 of them could line up across the width of a human hair. Inside that atom, the electrons are not zipping around like little planets. They are more like standing clouds, smeared out in particular shapes around the nucleus. These shapes are called orbitals, and they are not paths that the electron follows. They are more like maps of where the electron is likely to be found if you go looking for it. In one kind of orbital, the electron cloud is shaped like a sphere, surrounding the nucleus evenly on all sides. In another kind, it is shaped like a dumbbell, 2 lobes sticking out in opposite directions. In another, it is more like a clover leaf. These shapes are the electron's way of existing when it is part of an atom. Not a dot, not a path, a cloud of likelihood. And photons, the particles of light, are even stranger in their everyday behavior. A photon traveling through space is not a tiny bullet. It is a ripple, a disturbance in the electromagnetic field, spreading out as it goes. And yet, when it arrives at a detector, it arrives as a single point, a single click, a single flash. The wave-like behavior and the particle-like behavior are both real. They are both measured. They just show up in different circumstances. Learning to hold both ideas at once, without trying to force one to win, is part of the quiet mental shift that quantum physics invites. It is not a problem to be solved. It is a tension to be lived with. And that tension, that lived-with strangeness, is the soil in which entanglement grows. We are almost ready to meet entanglement directly, but first, we need to spend time with that cloud of possibilities. We need to understand what it means for a particle to be in a blend of states, a superposition. That is where we will go next. For now, let the atoms rest in the dark. Let the electrons drift in their clouds of maybe. Let the photons cross the vast distances between the stars, spreading out as waves and landing as points. The world of the very small is not a miniature version of our world. It is a different country, with different customs, different laws, different ways of being, and we are just visitors here. We do not need to master the language. We do not need to pass a test. We just need to look around, slowly, without hurry, and let the strangeness wash over us like quiet music, like the sound of rain, like the slow drift of clouds across a moonlit sky. The journey downward is complete for now. You have left the room. You have left the scale of beds and blankets and bodies. You are down among the atoms, down among the electrons and photons, down where the rules soften and the certainties fade. And that is a very good place to be. It is a place where the worries of the day cannot follow. They are too big. They belong to the world of tables and chairs. Down here, there is only the quiet hum of existence at its most fundamental level, the steady, patient dance of particles that have been here since the beginning of time. The same atoms in your body were forged in stars that lived and died long before the earth was born. The iron in your blood, the calcium in your bones, the oxygen in your lungs, all of it cooked in the hearts of ancient suns and scattered across space when those suns exploded. You are made of stardust, as the saying goes, but you are also made of quantum strangeness. Every atom in your body obeys the rules we are beginning to explore. The uncertainty, the cloud of possibilities, the wave-like and particle-like behavior, all of it is happening inside you, right now, in every cell, in every molecule. You do not feel it, just as you do not feel the motion of the earth spinning under your feet. But it is there. It is the ground of your being. And resting on that ground, letting the solidity of the big world dissolve into the fluidity of the small, can be a deeply peaceful thing. So breathe, and let yourself sink a little deeper into that thought. The world of the very small is not far away. It is right here. It is what you are made of. And the strangeness we are going to explore next, the blend of possibilities called superposition, is not a foreign oddity. It is the natural state of things at the deepest level. It is the way particles exist when they are not being watched. And that is where we are headed next, into the cloud, into the haze of maybe, into the quiet heart of quantum physics, where a single particle can be more than one thing at once, and where the act of looking changes what is seen. Let that thought rest with you as you drift. There is no rush. The words will continue in their own time. For now, just be here, down among the atoms, in the quiet dark, at the threshold of something strange and beautiful and profoundly calm. We are standing now at the threshold of something strange and beautiful and profoundly calm. The world of the very small is all around us, inside us, made of atoms and electrons and photons, particles that do not behave like marbles or baseballs. And the first deep strangeness we need to sit with, the one that opens the door to everything else, is this idea of a blend of possibilities. The idea that a single particle, before anyone looks at it, can be in more than one state at the same time. This is the cloud we are about to enter, the haze of maybe, the quiet heart of quantum physics. In everyday life, things are one way or another. A light switch is on or off. A door is open or closed. A coin on a table shows heads or tails. Those are the only options. There is no third state between on and off. There is no way for a coin to be both heads and tails at once. That is the common sense of the big world, and it is so deeply ingrained in us that we rarely even think about it. It just seems obvious. It seems like the way reality must work, at every level, down to the smallest pieces. But at the quantum level, reality does not work that way. At the quantum level, a particle can be in a state that is not simply one thing or the other. It can be in a blend, a combination, a mixture of possibilities that have not yet been sorted out. This blend is not a statement about what we know or do not know. It is not that the particle is secretly one thing or the other, and we just have not figured out which. According to quantum physics, the particle genuinely is in both states at once, in a very real sense, until something happens to force it to pick one. That something is usually a measurement, an observation, an interaction with something else that records or registers the particle's state. This blend of possibilities has a name. It is called superposition. The word comes from the idea of being placed over or laid on top of. A particle in superposition is not one thing on top of the other in physical space. It is more like the possibilities themselves are layered together, coexisting in the same particle at the same time, each one as real as the others, until the moment of measurement. We will use the word superposition from now on, but let it be a soft word in your mind, not a sharp technical term to be memorized, just a gentle label for a strange and quiet fact. Let us approach this with an image, not a perfect image. No everyday image is perfect for describing quantum behavior. The quantum world is not the everyday world, so any comparison we draw will be flawed at some level. That is fine. Flawed images can still be useful as long as we hold them loosely. Imagine a coin, an ordinary coin resting on a table. In the big world, the coin shows either heads or tails. If you close your eyes and someone flips the coin and covers it with their hand, you do not know which side is facing up. But the coin itself has a definite side. It is heads or tails. Your ignorance does not change the coin. Your lack of knowledge is just in your own mind. Now imagine a quantum coin, a coin that follows the rules of the very small. Before you look at it, this coin is not secretly heads. It is not secretly tails. It is not switching rapidly back and forth. It is in a superposition of heads and tails. Both possibilities are present. They coexist. They are layered together in a single state that has no everyday equivalent. It is only when you look, when you measure, when you interact with the coin in a way that records which side is up, that the superposition ends. The blend collapses into one definite outcome, heads or tails. And before that moment, there was no definite outcome at all, just the blend. That is a difficult idea to accept. It goes against every intuition we have built up over a lifetime of dealing with doors and switches and coins. And yet, this is what the mathematics of quantum physics describes, and this is what experiments, over and over, have confirmed. Particles at the quantum level really do behave as if they are in superpositions of possible states until they are measured. The blend is real. It is not just a gap in our knowledge. It is the way the world is built at its foundations. Let us make this a little more concrete. Particles have properties. An electron, for example, has a property called spin. Spin is not quite like a spinning top. It is not that the electron is physically rotating in space, but it is a form of built-in angular momentum, a kind of internal orientation that has measurable effects. The details of what spin really is are not important for us tonight. What matters is that spin, when measured along any given direction, can only take one of two values. Physicists call these values up and down, or sometimes plus and minus. The names are just labels. The point is that there are only two possible outcomes for a spin measurement, just as there are only two sides to a coin. Now, before you measure the spin of an electron, quantum physics says the electron can be in a superposition of up and down. It is not secretly up, it is not secretly down. It is in a blend of both. The blend is described by probabilities. The mathematics tells you, for example, that if you measure the spin along a certain axis, you have a 50% chance of getting up and a 50% chance of getting down. But those probabilities are not a sign of ignorance. They are not like saying, I do not know which side the coin landed on, so I will say 50-50. They are fundamental. The electron itself, before measurement, does not have a definite spin. It has a cloud of possible spins, a superposition, and the act of measuring forces it to show one definite result. This is the core idea. A particle can be in a superposition of different possible states. Each possible state is associated with a probability. The probabilities are not guesses, they are precise. They are calculated from the mathematical description of the particle, which is called its wave function. The wave function is a kind of map of all the possible states the particle could be found in, along with the likelihood of each. Before measurement, the wave function spreads out, encompassing multiple possibilities. When a measurement happens, the wave function appears to narrow down to a single outcome. This narrowing is sometimes called the collapse of the wave function, and what it really means, whether it is a physical process or just an update in our knowledge, is one of those open questions that physicists still debate. We will sit with that debate later. For now, just hold the basic picture. A particle before measurement is a cloud of maybe. A particle after measurement is a definite thing. This picture was not arrived at easily. It was worked out in the 1920s by a group of physicists who were themselves deeply puzzled by what they were finding. The mathematics was giving them clear answers, but the meaning of those answers was, and still is, hard to grasp. Werner Heisenberg, a German physicist, was one of the key figures. He developed a way of describing quantum systems that focused on what could actually be measured, and he showed that certain pairs of properties, like position and momentum, could not both be known with perfect precision at the same time. That is the uncertainty principle we touched on earlier. It is closely tied to superposition, because if a particle is in a superposition of many possible positions, then its position is not definite, and that is why you cannot pin it down. Another key figure was Erwin Schrödinger, an Austrian physicist. He developed a different way of describing quantum systems, using the idea of a wave that spreads out through space. His wave equation, the Schrödinger equation, describes how the wave function of a particle changes over time. It is a smooth, deterministic equation. It tells you exactly how the cloud of possibilities will evolve. The strangeness only appears when you try to connect the wave function to a definite measurement outcome. Then the smooth wave seems to jump, to collapse into a single point. Schrödinger himself was troubled by this. He came up with a famous thought experiment, a kind of parable, to highlight how strange the idea of superposition really is. You may have heard of it. It involves a cat in a box, and we will touch on it gently when the time is right. For now, just know that Schrödinger, one of the architects of quantum mechanics, spent much of his later life uneasy about what the theory seemed to imply. So superposition is not a fringe idea. It is built into the foundations of quantum physics by the very people who built the theory. And it is not just a mathematical trick. It has real, observable consequences. The interference patterns we see when electrons or photons pass through two slits, for example, only make sense if the particles are in superpositions of taking both paths at once. The whole field of quantum computing, which we will touch on much later, relies on the ability of quantum bits to be in superpositions of 0 and 1 at the same time. Superposition is a working, tested, practical feature of the world. It is as real as gravity, as real as electricity, as real as the warmth of your blanket. But what does it feel like to hold this idea in your mind? It feels strange, and that strangeness is welcome here. We are not trying to make it go away. We are not trying to explain it away with a clever analogy that makes it seem ordinary. It is not ordinary. It is the deep structure of reality, and it does not owe us the comfort of feeling familiar. We can simply let it be strange. We can let the strangeness wash over us without resistance. A particle, resting in the dark, is not one thing or another. It is a quiet hum of possibilities, a chord of maybes, and only when the universe asks it a question, only when something interacts with it in a way that forces a definite answer, does it become one thing. Before that, it is a blend, a cloud, a haze of potential. Think of an electron in an atom, one of those electrons we met in the last section. It is not racing around the nucleus in a neat little circle. It is smeared out in a cloud of possible locations. The shape of that cloud, the orbital, tells you where you are likely to find the electron if you go looking. But the electron, before you look, is not at any one of those points. It is in a superposition of being at all of them. The whole cloud is the electron. The electron is the whole cloud. That is why it cannot be pinned down to a single path. That is why the old picture of electrons as tiny planets orbiting a nuclear sun had to be abandoned. The reality is softer. It is more fluid. It is a superposition. And photons, the particles of light, can be in superpositions too. A photon can be in a superposition of different directions of travel, or different energies, or different polarizations, which is a property related to the orientation of its electric field. Polarization will become important later when we talk about the experiments that tested entanglement. For now, just know that the same rule applies. A photon before measurement can be in a blend of polarization states. It is not definitely polarized one way or another. It is a superposition. The coin image is useful, but let us refine it a little so it does not mislead us. A real coin, in the big world, cannot be in a superposition of heads and tails. The reason is that a real coin is made of trillions of atoms, and those atoms are constantly interacting with each other and with the environment. They are bumping into air molecules, absorbing and emitting photons of heat, jostling around. All those interactions act like tiny measurements. They force the atoms of the coin to have definite positions and definite orientations. The superposition gets washed away, constantly, by the sheer complexity of the big world. This is one of the reasons we do not see superpositions in everyday life. They are fragile. They only survive in isolation, when a particle is carefully shielded from anything that might measure it. In a coin, the isolation is impossible. The superposition is lost in an instant, too fast to notice. This process, the washing away of superpositions by interactions with the environment, is called decoherence. We will not spend much time on it tonight, but it is a helpful idea to have in the background. It explains why the quantum world and the classical world, the world of the small and the world of the big, can coexist. The quantum rules apply everywhere, but in big, complex objects, the superpositions are so fragile that they vanish almost instantly. We are left with the definite, either-or world we know. The strangeness is still there, underneath, but it is hidden by the constant chatter of interactions. So when we talk about a quantum coin, we are really talking about a single quantum particle, an electron or a photon, carefully isolated from the environment, held in a state where its superposition can survive. That is what makes the experiments we will discuss later so remarkable. The physicists had to learn how to create and preserve these fragile superpositions, and then entangle them, and then measure them, without letting the outside world wash the strangeness away. It took decades of careful work. It was not easy, and that patient, slow progress is part of the calm of this story. No one rushed. No one leapt to conclusions. They just kept refining their questions, one quiet step at a time. Now, as you lie here in the dark, you might wonder whether this applies to you. Are you in a superposition? Is your body, made of trillions of atoms, somehow a cloud of possibilities? The answer, as best as we understand it, is no. Not in any practical sense. You are too big, you are too warm, you are too deeply entangled with your environment, constantly exchanging photons and air molecules in heat, for any quantum superposition to survive across your whole body. You are a definite thing, in a definite place, at a definite time, and that is good, that is restful. The strangeness is down at the bottom, in the individual particles that make you up. It does not bubble up to the level of your conscious experience. You can rest easy in your definiteness, while knowing, in some abstract, gentle way, that your foundations are fluid. But let us not drift too far from our main path. Superposition is the first key. It is the idea that a particle can be in a blend of possible states until it is measured. This blend is described by probabilities. It is not a gap in our knowledge. It is the way the particle actually is. And it was discovered and formalized in the 1920s by physicists like Heisenberg and Schrödinger, who were themselves deeply puzzled by what they had found. Why does this matter for entanglement? Because entanglement is what happens when two particles are in a superposition together. Not separate superpositions, a joint superposition, a shared cloud of possibilities that links them so that the state of one cannot be described without the state of the other. That is where we are going. We are almost ready to open that door. But first, let superposition settle a little deeper. Let it become a familiar strangeness, a known unknown, something you can hold in your mind without gripping it tightly. Imagine a single electron, alone in the dark, held in a vacuum chamber by gentle electromagnetic fields. It is not being measured. It is not being watched. Its spin is in a superposition of up and down. Both possibilities are equally real. The electron does not need to decide. It simply exists, quietly in its blend. There is no contradiction in its existence. The contradiction only arises when we try to force it into our everyday categories. If we insist that something must be either up or down, then the electron in superposition seems impossible. But if we let go of that insistence, if we allow that reality at its deepest level might be more fluid than our categories, then the electron in superposition is not a problem. It is just a fact. A quiet, steady fact, as natural as gravity, as unbothered as starlight. That letting go is the heart of the calm we are cultivating here. Not understanding everything, not forcing the pieces to fit, just letting the world be as it is, strange and precise and deeply, deeply peaceful. The electron, in its cloud of maybe, is not anxious. It is not trying to figure itself out. It is simply there, in its full quantum reality, waiting for nothing. You, lying in the dark, can borrow some of that peace. You do not need to figure everything out tonight. You do not need to resolve your own superpositions, whatever they may be. You can simply rest, as the electron rests, in the quiet acceptance of what is. The story will continue. We will take the next step soon. We will see what happens when two particles share a superposition, when their possibilities become linked in a way that survives across distance. That is entanglement, and it is built directly on the foundation we have just laid. A particle can be in a blend of possibilities. Two particles can be in a blend together, and from that simple step, a universe of mystery unfolds. But it unfolds slowly. It unfolds calmly. There is no rush. For now, just the blend, just the cloud, just the single particle, alone in the dark, being more than one thing at once, and not minding at all. We left a single particle resting in the dark, alone, being more than one thing at once, and not minding at all. A quiet cloud of maybe, a blend of possibilities. That was superposition, and it is beautiful on its own, a strange and peaceful fact about the very small. But now we take the next step. Now we see what happens when two particles share that cloud, when their possibilities become linked, not separately, but together. This is entanglement. This is the quiet heart of our story. Let us begin simply. Imagine two particles. They could be two electrons. They could be two photons, two tiny pieces of light. They are created together or they interact in some way that links them, and then they move apart. They travel in different directions. They cross the room, they cross the city, they cross the space between the stars. And yet, despite the distance, they are not separate in the way that two marbles are separate. Their properties are connected, their states are shared. If you measure one of them, you instantly learn something about the other, not because a signal traveled from one to the other, not because they sent a message across the gap, but because they were never truly separate to begin with. They are two parts of a single quantum system. That is the core definition of entanglement. Two particles can be created or linked in such a way that their properties stay connected, no matter how far apart they later become. The connection is not a physical string, it is not a force field, it is a shared state, a joint superposition. The particles are described by a single wave function, a single cloud of possibilities that covers both of them at once. And that cloud does not break apart when the particles move away from each other. It stretches, it remains whole, it remains one thing, even as the distance grows. Let us make this more concrete. Suppose we have two particles, and each one has a property called spin, which we talked about in the last section. Spin, when measured, can be up or down. That is the only choice. Now these two particles are created in a special way, so that their spins are linked. The link is this. If one particle is measured and found to be spin up, the other particle, if measured, will always be found to be spin down, always, 100% of the time, and the other way around. If the first is down, the second is up. They are perfectly anti-aligned. They are opposites, always and forever. Now, here is the strange part. Before anyone measures them, neither particle has a definite spin. Each one is in a superposition of up and down. That is what we learned in the last section. A single particle, on its own, is a blend. But these two particles are not on their own. They are entangled. And their superpositions are not independent. They are woven together. The blend is a shared blend. It is not that particle A is maybe up and maybe down, and particle B is separately maybe up and maybe down. It is that the pair together is in a superposition of A up and B down, and A down and B up. Those are the two possibilities that coexist. The possibility of A up and B up is not there. The possibility of A down and B down is not there. The only possibilities are the ones where they are opposites. So before measurement, the pair is in a quiet, shared haze. Neither particle has a definite spin, but their fates are tied together. They are linked. They are entangled. Now someone measures particle A. The measurement forces particle A to leave its superposition and become definite. It shows up, or down. The moment that happens, the shared cloud collapses. And particle B, no matter where it is, no matter how far away, instantly becomes definite too. Not because it was secretly down all along. Before the measurement, it was not secretly anything. It was in the shared superposition. But now that the measurement on A has happened, B must take the opposite value. If A is up, B is down. If A is down, B is up. And this correlation holds. It has been tested. It is real. Notice what did not happen. No signal was sent from A to B. No little message flew across the space between them. The person measuring A did not choose the outcome. The outcome was random, a 50-50 chance, just as quantum physics predicts for a superposition. You cannot force A to come out up. You cannot use A to send a message to B. All you can do is measure A, get a random result, and then know, instantly, what someone measuring B will find. That is correlation, not communication. We will return to this point later when we gently correct some common misunderstandings. For now, just hold the core image. Two particles, linked at creation, their properties correlated, no matter the distance. Measuring one tells you about the other. The link is real. The link is tested. The link is called entanglement. The word entanglement itself has a quiet beauty. It suggests threads wound together, fibers twisted into a single cord, something that cannot be pulled apart without losing what it is. The physicist who coined the term was Erwin Schrödinger, the same Schrödinger we met in the last section, the one who gave us the wave equation and the famous cat. In 1935, Schrödinger wrote a paper in which he used the German word Verschränkung, which translates to entanglement or cross-linking. He was responding to a paper by Einstein and his colleagues, which we will explore in the next section. Schrödinger saw that entanglement was the central feature that made quantum physics different from classical physics. He called it not one, but rather the characteristic trait of quantum mechanics. He understood, early on, that this linked state was the key to the whole puzzle. So the concept has been with us for a long time, almost a century. It is not a new discovery. It is a settled, well-understood feature of the quantum world. What has changed over the decades is our ability to test it, to probe it, to use it. But the basic idea was there from the start, in the mathematics and in the minds of the physicists who first wrestled with it. Let us sit with the image a little longer, letting it soften and settle. Two particles, born together, then separated. One goes left, one goes right. They travel for miles, for light years, for eons. They have no communication device. They have no hidden transmitters. And yet, when you measure one, the other seems to know what to do. Not because it is told, not because it is signaled, but because the measurement of one is also, in a sense, a measurement of the pair. The pair was always one thing, described by one wave function. The act of measurement does not break a connection that was maintained by signals. It simply reveals a connection that was always there, woven into the fabric of the particle's existence. This is a difficult idea to hold in the mind, because our minds were built for separate objects. We see two marbles, and we think, two separate things. And for marbles, that is correct. But quantum particles are not marbles. They are not separate in the same way. When two particles are entangled, the very idea of particle A and particle B as independent objects becomes fuzzy. They are better thought of as two aspects of a single extended quantum system. The system has parts that are located in different places, but those parts are not independent. They are bound together by the shared wave function. The wave function lives in a mathematical space that does not care about physical distance. It treats the two particles as a single entity, no matter how far apart they are. And when that single entity is measured, it responds as a whole. Think of a pair of gloves. A left glove and a right glove. Someone puts them in two separate boxes without showing you which is which. They mail one box to you and one box to a friend on the other side of the world. You open your box and find the left glove. Instantly, you know your friend has the right glove. There is no mystery here. No spooky action. The gloves were always a pair. The information was set from the start. This is a classic analogy for entanglement, and it is useful because it captures the idea of correlation. But it is also deeply misleading, because it suggests that the particles had definite properties all along, just hidden in the box. That is exactly what entanglement is not. In the glove analogy, your box always contained the left glove. You just did not know it. In quantum entanglement, before you open the box, the particle does not have a definite handedness. It is in a superposition. The glove analogy misses the superposition. It misses the cloud of maybe. Entanglement is superposition shared between two particles. That is what makes it different from ordinary correlation. So the glove analogy is a stepping stone. Step on it gently and then leave it behind. The real thing is stranger. The real thing is this. Before measurement, neither particle has a definite spin. Both are in a shared cloud. The measurement of one does not reveal a pre-existing fact. It seems to bring a fact into being, a fact that instantly applies to both particles, no matter the distance. That is the mystery. That is the not knowing that even physicists sit with. But let us not rush into the mystery too quickly. Let us first appreciate the fact itself. Entanglement is real. It has been created in laboratories thousands of times. Pairs of entangled photons are produced by shining lasers through special crystals. Pairs of entangled electrons are produced in carefully designed solid-state devices. The particles are separated, sometimes by meters, sometimes by kilometers, and their correlations are measured. The correlations match the predictions of quantum physics with stunning precision. This is not speculation. This is not philosophy. This is experimental science, repeated and confirmed. And yet, the experience of learning about it for the first time can feel like a kind of slow astonishment. That is natural. That is allowed. Let the feeling be there. Let it wash over you, gently, without gripping it. Two particles, separated by distance, still connected. It is like a quiet poem written into the laws of nature, a reminder that separateness is not the deepest truth, a hint that the world, at its foundations, is more unified than it appears. We can also think about entanglement in terms of what physicists call measurement outcomes. Suppose you and a friend each have a detector, far apart. A source in the middle sends out entangled pairs of photons, one toward you, one toward your friend. You each measure the polarization of your photon. Polarization is a property of light, related to the orientation of the electric field. Like spin, it can take one of two values when measured along a given axis. You might measure vertical or horizontal. Your friend might measure vertical or horizontal. If the photons are entangled in a particular way, the results will be correlated. When you measure vertical, your friend, if they measure along the same axis, will also find vertical. When you measure horizontal, they will find horizontal. The results match, every time. But neither of you can predict, in advance, what your own result will be. It is random, 50-50. Only when you compare notes, later, using ordinary signals that travel no faster than light, do you see the pattern. The pattern is perfect correlation. The pattern is entanglement. This is the core of the matter. Entanglement is a correlation between measurement outcomes that is stronger, in a precise mathematical sense, than any correlation that could be explained by pre-existing properties. We will unpack that idea more when we talk about John Bell and the experiments that tested his ideas. For now, just let the basic picture settle. Two particles, linked. Measurement outcomes correlated. No signals traveling, just a shared state, a joint superposition, a single quantum system stretched across space. And now, as you lie here in the dark, let the image expand a little. Think about what this means for the idea of separation. In our everyday lives, we think of things as separate. You are in your bed. The walls are around you. The world outside is outside. The stars are far away. All of that is true, at the level of everyday experience. But underneath that experience, at the level of the particles that make up everything, the boundaries are softer. The separations are less absolute. Particles that were once together can remain connected, in a very real sense, even after they have traveled to opposite ends of the universe. The connection is not a practical one. You cannot use it to send a message. You cannot use it to influence anything. But it is there. It is a fact about the structure of reality. And that fact, held gently in the mind as you drift towards sleep, can feel like a quiet comfort. A reminder that isolation is not the whole story. That connection is woven into the fabric of things. Schrödinger saw this in 1935. He gave it the name entanglement, and he understood that it was the central puzzle of quantum physics. He wrote that if two particles are entangled, the best possible knowledge of the whole does not include the best possible knowledge of its parts. In other words, you can know everything there is to know about the pair, and still know nothing definite about each individual particle. The whole is more certain than the parts. The whole is the primary reality. The parts are secondary, derived, dependent on measurement. That is a profound shift in perspective. It inverts our usual way of thinking. Usually, we start with the parts and build up to the whole. Here, the whole comes first. The pair is the fundamental unit. The individual particles are just ways that the whole can manifest when we poke it with a measurement. Let that thought rest with you for a moment. The whole comes first. The pair is the fundamental unit. It is a thought that applies, in its own way, far beyond physics. It is a thought about belonging, about connection, about the deep structure of existence. You do not need to analyze it. You do not need to draw any conclusions from it. Just let it be there, a quiet companion in the dark. We have now laid the foundation. We understand superposition. We understand entanglement. The next step is to see how this idea was received, historically, by the people who first encountered it. Because not everyone was comfortable with it. In fact, one of the greatest physicists of all time found it deeply troubling. He called it spooky action at a distance, and he spent years trying to show that it could not be the whole story. His discomfort is part of our story too. It humanizes the mystery. It reminds us that even geniuses struggle with the strangeness of the quantum world. And it sets the stage for the quiet, patient work that eventually turned a philosophical debate into a testable scientific question. But that is for the next section. For now, just the entanglement. Just the two particles, linked, drifting apart in the dark, still one thing, still connected, still holding their shared secret across whatever distance grows between them. Let that image be the last thing in your mind as you slip a little deeper towards sleep. Two particles, born together, never truly separate. A quiet reminder that the universe, at its smallest scale, does not insist on isolation. It allows for connection. It is built for connection. And that is a restful thought to carry with you into the night. That restful thought, the image of two particles born together and never truly separate, was not restful to everyone. In fact, it was deeply troubling to one of the greatest physicists who ever lived. His name was Albert Einstein, and his discomfort with entanglement is part of our story. It humanizes the mystery. It reminds us that even the most brilliant minds can find themselves unsettled by what the universe seems to be saying. And it shows us that genuine scientific disagreement, pursued with patience and rigor, can be a gift. It can sharpen the questions. It can lead, eventually, to deeper understanding. Einstein had been one of the architects of quantum physics in its early days. In 1905, the same year he published his theory of special relativity, he also wrote a paper explaining the photoelectric effect, the way light knocks electrons out of a metal. In that paper, he proposed that light comes in discrete packets of energy, which we now call photons. This was one of the founding insights of quantum theory. Einstein was not an outsider to this new physics. He was there at the beginning, helping to build it. But as quantum mechanics developed through the 1920s, Einstein grew more and more uneasy. The theory worked. It made predictions that matched experiments with extraordinary precision. But it seemed to describe a world in which fundamental reality was uncertain, probabilistic, governed by chance rather than by definite causes. A particle did not have a definite position or a definite spin until it was measured. The outcome of a measurement was not determined in advance. It was random, with only probabilities to guide it. This bothered Einstein deeply. He believed that the world, at its deepest level, should be orderly and deterministic. He believed that if you knew everything about a system at one moment, you should be able to predict everything about it at all future moments. The randomness of quantum mechanics seemed to him a sign that the theory was incomplete, that it was missing something, that there must be hidden factors, hidden pieces of the puzzle that would restore order and certainty if only we could find them. This was not stubbornness for its own sake. It was a philosophical conviction rooted in a lifetime of thinking about how the universe works. Einstein often said things like, "God does not play dice with the universe." He did not mean this in a religious sense, not exactly. He meant that the fundamental laws of nature should not be based on chance. They should be based on certainties. A cause should lead to a definite effect, not a range of possible effects with different odds. That was his intuition, and intuitions, even the intuitions of geniuses, can be right or wrong. They have to be tested. They have to be brought before the court of experiment. But they are valuable. They drive the search for deeper understanding. Einstein's discomfort drove him, and others, to ask sharper questions about quantum mechanics. And those questions led, in time, to the experiments that confirmed entanglement beyond any reasonable doubt. Let us step into the year 1935. Einstein was living in Princeton, New Jersey, having fled the rise of the Nazi regime in Germany. He was working at the Institute for Advanced Study, a place designed to give great thinkers the time and space to think. He was not alone in his unease about quantum mechanics. He found two collaborators who shared his concerns. One was Boris Podolsky, a Russian-born physicist. The other was Nathan Rosen, a younger physicist who had been one of Einstein's assistants. Together, the three of them wrote a paper. It was published in the journal Physical Review in May of 1935. Its title was, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" And it is known to this day as the EPR paper, after the initials of its three authors, Einstein, Podolsky, and Rosen. The EPR paper was not a rant. It was not an emotional plea. It was a careful, logical argument, laid out step by step. It did not question that quantum mechanics worked as a calculational tool. The authors acknowledged that the theory made correct predictions. What they questioned was whether the theory gave a complete description of reality. They proposed a criterion for completeness. If a physical theory is complete, they argued, then every element of physical reality must have a counterpart in the theory. And what is an element of physical reality? They proposed a simple test. If you can predict, with certainty, the value of a physical quantity without disturbing the system in any way, then that quantity corresponds to an element of reality. So far, so calm. This was just careful thinking. Then they applied this reasoning to a pair of particles that had interacted and then separated. They showed that, according to quantum mechanics, you could measure one particle and thereby predict, with certainty, the corresponding property of the other particle, even if the two particles were far apart and the measurement on the first one could not possibly disturb the second one. Therefore, they argued, the property of the second particle must be an element of reality. But quantum mechanics did not assign a definite value to that property before the measurement. It only assigned a probability. Therefore, quantum mechanics must be incomplete. There must be something else, something not captured by the wave function, that determined the outcome. The EPR paper was written in a dense, careful style, but the core idea can be stated in plain words. If two particles are entangled, and you measure one, you instantly know something about the other, no matter the distance. This seems to imply that the second particle had that property all along, even before the measurement. If it did not have the property all along, then how did it know what value to show? How did the information travel from one particle to the other, faster than light? That seemed impossible, according to Einstein's own theory of special relativity, which said that no signal could travel faster than light. So the only reasonable conclusion to Einstein and his colleagues was that the particles must carry some hidden information with them from the moment of their creation. Information that told them what value to show when measured, information that was simply not included in the quantum mechanical description. This proposed hidden information came to be known as hidden variables. The idea is simple and appealing. The particles are like a pair of gloves, as we mentioned in the last section. One is a left glove, one is a right glove. They are separated and sent to different places. When you open the box and find a left glove, you instantly know the other is a right glove. No mystery, no spooky action. The gloves had their handedness from the start. The only reason quantum mechanics seemed mysterious, Einstein argued, was that it refused to admit the existence of the hidden handedness, the hidden variables, that determined the outcome. The theory described the particles with probabilities because it was ignorant of these hidden factors. It was like describing a coin toss with 50-50 odds, not because the coin is genuinely both heads and tails, but because you do not know the exact forces acting on the coin as it flips. If you knew those forces precisely, you could predict the outcome with certainty. Quantum mechanics, in Einstein's view, was like that, a statistical summary of a deeper, more deterministic reality. This was a genuine scientific disagreement. It was not Einstein being stubborn for no reason. It was not Einstein failing to understand quantum mechanics. He understood it very well. He just believed it was a stepping stone to something more complete. He believed that the universe, at its foundations, should make sense in a way that quantum mechanics did not. The idea of a measurement on one particle instantly affecting another, arbitrarily far away, struck him as absurd. He used a phrase that has echoed through the decades. He called it spooky action at a distance. In German, spukhafte Fernwirkung. He meant it as a gentle mockery, a way of saying, surely you cannot believe this is how the world actually works. And many physicists agreed with him, at least in part. The EPR paper sparked a debate that has never fully ended. Niels Bohr, one of the founders of the Copenhagen interpretation of quantum mechanics, wrote a response defending the completeness of the theory. Schrödinger, as we heard, coined the term entanglement in his own response, acknowledging that the EPR paper had identified something profoundly strange. The debate was vigorous but respectful. It was conducted in the pages of journals, in letters, in conversations at conferences. It was not a shouting match, it was a slow, careful exchange of ideas, each side trying to understand the other, each side convinced that the other was missing something essential. And for about 30 years, the debate remained philosophical. It seemed impossible to test. Everyone agreed on what the experiments would show. Everyone agreed on the mathematical predictions. The disagreement was about what those predictions meant. Did they mean that reality was inherently uncertain, with genuine randomness and a kind of non-local connection between entangled particles? Or did they mean that quantum mechanics was incomplete, and that a deeper theory, one with hidden variables, would restore determinism and local causality? Local here means that things can only affect other things that are nearby, and any influence must travel through space at a finite speed, no faster than light. Einstein was a firm believer in locality. It was built into his theory of relativity. The idea of an instantaneous influence across a distance, a spooky action at a distance, seemed to him a violation of the deepest principles of physics. So the stage was set. On one side, the quantum mechanics of Bohr, Heisenberg, and Schrödinger, which accepted superposition, entanglement, and the inherent role of measurement in bringing definite outcomes into being. On the other side, the skepticism of Einstein, Podolsky, and Rosen, who believed that there must be hidden variables, preset properties that explained the correlations without any need for spooky action. For decades, it seemed like a philosophical standoff. No one could think of an experiment that would tell the difference. But that is the thing about patient, careful thinking. Sometimes it opens doors that no one expected. Sometimes a quiet insight, pursued over years, can turn a philosophical debate into a testable question. That is what happened next, and the person who made it happen was a physicist named John Stuart Bell. He was not one of the famous names of early quantum mechanics. He worked in relative quiet in the 1960s, thinking deeply about the foundations of the theory, and he found a way, a beautifully simple way, in principle, to ask nature herself whether Einstein's hidden variables could explain entanglement, or whether something stranger was going on. But that is for the next section. For now, let us stay with Einstein's discomfort a little longer. Let us sit with the idea that even someone of his stature could lie awake at night, troubled by what the universe seemed to be telling him. He never fully accepted quantum mechanics. He spent his later years working on a unified field theory, a grand synthesis that he hoped would restore order and determinism to physics. He did not succeed in that quest, but his discomfort, his persistent questions, were not a waste. They were a gift. They pushed other physicists to think more clearly, to ask sharper questions, to look for ways to test what seemed untestable. The EPR paper, which was meant to show that quantum mechanics was incomplete, ended up providing the conceptual framework that allowed Bell to formulate his famous test. Einstein would not have liked the outcome of that test, but he would have respected the process. Science is not about being right. It is about asking questions and following the evidence, even when it leads somewhere unexpected. So as you lie here in the dark, you might feel a kinship with Einstein's discomfort. You might find yourself thinking that entanglement seems impossible, that there must be some hidden trick, some missing piece that would make it all make sense. That is a very human response. It is the response of a mind that has spent a lifetime in a world of separate objects and definite properties. Do not fight it, just let it be there. The discomfort is part of the calm. It is the feeling of a mind stretching, reaching the edges of its usual categories, and finding something beyond them. That stretching is not painful. It is gentle. It is like a muscle being slowly, carefully flexed after a long day. It can even be pleasant if you let it. Imagine Einstein himself, in his study in Princeton, late at night. The room is quiet. A lamp casts a pool of light on his desk. He is thinking about two particles, separated by a great distance, still somehow connected. He does not like it. He scribbles notes. He writes letters to his colleagues. He tries to find the flaw, the hidden assumption, the way out. He is not angry. He is not upset. He is just deeply, persistently curious. And that curiosity, that refusal to let go of a puzzle, is one of the most beautiful things about science. It is not about certainty. It is about the patient, quiet pursuit of understanding. And sometimes that pursuit takes a lifetime. Sometimes it is passed on to the next generation, and the next. The questions Einstein asked in 1935 were not fully answered until decades later, when technology caught up with theory and the experiments could finally be done. And what were those experiments? What did they find? We will get there. We will walk through them calmly, step by step. But first we need to understand the key insight that made them possible. The insight of John Bell. The realization that there was a way, a clever way, to tell the difference between Einstein's hidden variables and the stranger reality of quantum mechanics. That is where we are going next. And the path there is quiet and well lit. No rush, no drama. Just the slow unfolding of an idea that changed how we think about the universe. For now, rest with Einstein's ghost, with his discomfort, with his stubborn, beautiful belief that the world should make sense, and with the quiet acknowledgement that the world, at its deepest level, might not make sense in the way we expect. It might be stranger. It might be more interconnected. It might be spooky, in the best and calmest sense of that word. And that is fine. That is more than fine. That is the quiet wonder at the heart of things. Let it be there, in the dark with you, as you drift a little further from wakefulness. Einstein asked his questions. Bell found his answer. And we, lying here in the quiet, get to follow the thread from one to the other, without hurry, without pressure, just the gentle movement of a story that has been unfolding for almost a century and is still, in its deepest meanings, not fully told. Einstein asked his questions, and for a long time they seemed unanswerable. The debate between Einstein and the quantum physicists, Bohr and Heisenberg and the rest, sat in the realm of philosophy. It was a discussion about what the mathematics meant, not about what the experiments would show. Everyone agreed on the predictions. Everyone agreed on what you would see if you measured an entangled pair. The disagreement was about whether those measurements revealed a deeper reality of hidden variables, preset properties carried by the particles from birth, or whether they revealed something stranger, something genuinely uncertain and interconnected at the foundations of the world. And for about 30 years, that was where the matter rested, a philosophical standoff, polite and unresolved. Then, in the 1960s, a physicist named John Stuart Bell entered the story. Bell was not a loud or famous figure. He was a quiet man from Northern Ireland, born in Belfast in 1928. He studied physics at Queen's University Belfast, and then he went on to work in particle physics and accelerator design at the European Organization for Nuclear Research, better known as CERN. But his deep passion, the thing he thought about in his spare time, was the foundations of quantum mechanics. He was fascinated by the EPR paper and the questions Einstein had raised, and unlike most physicists of his time, who had moved on to other problems, Bell believed there might be a way to settle the debate. Not with more philosophy, not with more arguments about what the mathematics meant, but with an actual experiment. What Bell did, in a paper published in 1964, was remarkable. He found a way to turn Einstein's philosophical discomfort into a testable question. He derived a mathematical relationship, an inequality, that would have to hold true if Einstein's vision of the world was correct. If the world was made of particles carrying hidden, preset properties, and if those properties were local, meaning they could not be influenced instantly by things happening far away, then the correlations between entangled particles would have to obey a certain limit. They could not exceed a particular bound. Quantum mechanics, on the other hand, predicted that the correlations would exceed that bound. They would be stronger than any local hidden variable theory could possibly explain. This was the key insight. The two views of the world made different predictions, not about individual outcomes, but about the statistical pattern of many outcomes. And that difference could be measured. Let us sit with this slowly. It is the quiet turning point of our story. Bell's insight was not about a single measurement on a single pair. It was about a pattern that would emerge over many, many trials. If you create thousands of entangled pairs, and you measure them in different ways, varying the angle of your detectors, the hidden variable theories and quantum mechanics give you different answers for how often the results should match. Quantum mechanics says they should match more often than any local hidden variable theory allows. The difference is subtle. It is not something you would notice by looking at one pair, but if you run the experiment enough times, the statistics speak clearly. Bell's result is known as Bell's theorem, though the word theorem might sound sharper than we need tonight. Think of it as Bell's question, a question posed to nature in the language of mathematics. The question was this: do the correlations between entangled particles respect the limit set by local hidden variables, or do they exceed it, as quantum mechanics predicts? If they respect the limit, then Einstein's intuition was right. The particles carry hidden properties, and no spooky action at a distance is needed. If they exceed the limit, then something stranger is going on. The world is not locally real, as the phrase sometimes goes. Either hidden variables do not exist, or locality, the idea that distant things cannot influence each other instantly, must be given up, or both. This is a good place to pause and talk about locality in plain terms. Locality is an idea so basic to our everyday experience that we rarely even notice it. It says that things can only affect other things that are nearby, or that influence must travel through the space between them at a finite speed. If you want to move a cup on a table, you have to touch it, or blow on it, or use a stick, or in some other way bridge the gap between you and the cup. The influence travels from your hand to the cup across the space between them. In the big world, this is always true. Even gravity and light, which can reach across vast distances, take time to travel. The sun's light takes about 8 minutes to reach the Earth. The sun's gravity takes the same time. If the sun vanished in an instant, the Earth would continue in its orbit for 8 minutes before the change in gravity arrived. Influence is local. It travels through space at a finite speed. This is a cornerstone of Einstein's theory of relativity. Bell's question asked whether this cornerstone holds at the quantum level. Are entangled particles like the sun and the Earth, communicating their correlations through some signal that travels between them? Or are they correlated in a way that cannot be explained by any signal, no matter how fast? If the correlations exceed Bell's limit, then no local signal, no preset hidden variables, can account for them. The connection would be, in a very precise sense, non-local. It would not be a signal, it would not be a force, it would be something else entirely, something that does not fit into our everyday categories. Bell himself did not build the experiment. He was a theorist. He worked with equations and ideas. But his paper, published in a relatively obscure journal called Physics Physique Physica, did not go unnoticed forever. Slowly, over the next decade, experimental physicists began to take up the challenge. They realized that Bell's question could be asked in a real laboratory, with real photons and real detectors. The technology was not quite ready in 1964, but it was getting close. Lasers were becoming more reliable, single photon detectors were being developed. The pieces were falling into place. Before we follow the experimenters into the laboratory, let us spend a little more time with Bell's question itself. Let us understand, in a gentle and approximate way, what it was that he asked. We do not need equations, we just need the shape of the idea. Imagine you and a friend are playing a strange game. A source in the middle of the room sends out pairs of particles, one to you, one to your friend. You each have a detector with a dial. The dial can be set to one of three positions. Let us call them position 1, position 2, and position 3. For each pair of particles, you choose a dial setting at random, and your friend chooses a dial setting at random. You each record whether your particle came out as spin up or spin down, or in the case of photons, whether the polarization was vertical or horizontal. You do this for thousands and thousands of pairs. At the end, you compare notes. You look at the cases where you both happen to choose the same dial setting. In those cases, because the particles are entangled, you always find opposite results. If you got up, your friend got down. If you got vertical, your friend got horizontal. Perfect anti-correlation. No mystery there. That is just the entanglement we already understand. The interesting part comes when you chose different dial settings. Suppose you chose setting 1 and your friend chose setting 2. How often do your results disagree? Quantum mechanics gives a specific answer, based on the angle between the settings. Hidden variable theories give a different answer. They give an answer that must satisfy Bell's inequality, a mathematical bound on how often the results can disagree across all the different combinations of settings. If the actual disagreements, measured in the laboratory, stay within that bound, hidden variables win. If they exceed the bound, quantum mechanics wins. The bound itself is not something we need to calculate tonight. It is enough to know that it exists. Bell found a way to put a number on the maximum correlation that local hidden variables could produce. Quantum mechanics predicted a number higher than that maximum. The two numbers are different. They cannot both be right. One view of the world must be incorrect, not approximate. Not incomplete, incorrect. The experiments would decide. This was a profound shift. For the first time, a question about the deepest nature of reality had been brought into the realm of experimental science. It was no longer just a matter of opinion or interpretation. It was a matter of measurement. You could build the apparatus, run the trials, count the outcomes, and see which view of the world the data supported. This is science, at its quietest and most patient. Not a sudden breakthrough, not a dramatic announcement. Just a careful question, posed precisely, and a steady effort to find the answer. Bell's question also sharpened our understanding of what entanglement is not. It is not a signal, it is not a force that travels from one particle to the other. Bell's inequality is a way of proving that the correlations are not caused by any communication between the particles, because if they were, the correlations would have to obey a different pattern. The pattern we actually see, as we will learn in the next section, is the pattern of quantum mechanics. It is the pattern of a world where separateness is not fundamental, where the whole is more real than the parts, where something that looks like instantaneous coordination is woven into the fabric of things. But let us not get ahead of the experiments. For now, just Bell. Just his quiet insight. John Stuart Bell, working in his spare time, thinking about a question that most physicists had set aside, found a way to ask nature a question she could answer. He did not know, when he published his paper, whether anyone would ever be able to perform the experiment. The technology was difficult, the measurements were delicate, many things could go wrong, but he had opened a door. He had shown that the debate between Einstein and Bohr was not just philosophy, it was physics. It could be tested. And that is a restful thought in its own way. The idea that even the deepest mysteries, the questions that seem to be matters of pure opinion, can sometimes be brought down to earth and measured. Not always, not in every area of life. There are mysteries that remain mysteries, questions that cannot be settled by any experiment. But in this case, for this particular mystery, a quiet man with a pencil and paper found a crack in the door. He pried it open, and the light that came through that crack has been growing ever since. Bell died in 1990, relatively young, at the age of 62. He did not live to see the full flowering of the field he helped create. He did not see the Nobel Prize awarded to the experimenters who confirmed his predictions. But his name is permanently attached to one of the most important ideas in the history of physics: Bell's theorem, Bell's inequality, Bell's question, the quiet question that changed everything. As you lie here in the dark, you might think of Bell as a kind of patron saint of quiet curiosity. He was not seeking fame, he was not trying to overturn the world, he was just puzzled by something, and he kept picking at it, in the margins of his regular work, until he found a way to make the puzzle testable. That is a very calm way to do science. It is a very calm way to live. Not with urgency, not with the need to be right, but with the steady patience of someone who knows that understanding takes time, and that even the smallest insight can, decades later, illuminate the universe. Bell's question is still being asked, in more refined forms, in laboratories around the world. Each new experiment closes a few more loopholes, tightens a few more constraints, confirms with ever greater precision that the world does not obey local hidden variables. The answer is in. The universe is not locally real, in the sense Einstein hoped, but the question continues to bear fruit. It has led to new technologies, new ways of processing information, new insights into the nature of space and time. A quiet question, asked in earnest, can ripple outward forever. We are now ready to follow that ripple into the laboratory. In the next section, we will meet the experimenters: John Clauser, Alain Aspect, Anton Zeilinger, and others. We will see how they took Bell's question and turned it into a real apparatus, with lasers and crystals and detectors and careful counts of photons. We will see what they found, and we will let the weight of that finding settle over us, not as a dramatic revelation, but as a quiet confirmation of something we have been building toward all along. The world is entangled, the connections are real, and the not knowing about what that ultimately means is still with us, calm and patient, waiting for the next quiet question to be asked. Bell asked his question. He put it on paper in 1964, in a quiet journal, in the language of mathematics. And then the question sat there, waiting. It waited for technology to catch up. It waited for someone with the right skills and the right patience to pick it up and carry it into the laboratory. That someone, the first to take up the challenge, was a physicist named John Clauser. John Clauser was a graduate student at Columbia University in the 1960s when he first encountered Bell's paper. He read it, and he was fascinated. Here was a question that had seemed purely philosophical, a matter of interpretation and opinion, and Bell had shown that it could be tested. You could actually do an experiment and get an answer. The universe would tell you, in its own quiet way, whether Einstein's hidden variables were real or whether the strangeness of quantum entanglement was here to stay. Clauser decided that he wanted to be the one to ask the question directly. But wanting to do the experiment and actually doing it were two different things. The technology of the 1960s was not quite ready. You needed a source of entangled particles. You needed detectors that could measure single photons. You needed a way to change the measurement settings quickly and randomly. And you needed to do all of this with enough precision to see the subtle statistical difference that Bell had predicted. It was a tall order. Clauser had to build much of the equipment himself. He had to scrounge for parts. He had to work in a small laboratory at the University of California, Berkeley, with a limited budget and a lot of skepticism from colleagues who thought he was wasting his time on a fringe question. But he persisted. With the help of a graduate student named Stuart Friedman, Clauser designed and built an experiment that used entangled photons. The photons were produced by a process called atomic cascade, in which calcium atoms were excited by a lamp and then emitted pairs of photons, one after the other, whose polarizations were entangled. The photons were sent to two separate detectors, each of which could measure the polarization at different angles. Clauser and Friedman ran the experiment over and over, collecting data, counting photons, looking for the pattern that would tell them whether Bell's inequality was violated or not. The experiment was not perfect. The technology was crude by later standards. The detectors were slow. The source of entangled photons was not as bright as they would have liked. There were loopholes, meaning possible ways that the results could be explained without giving up local hidden variables, if you assumed certain imperfections in the apparatus. Clauser and Friedman were aware of these loopholes. They did the best they could with the tools they had, and in 1972 they published their results. The data violated Bell's inequality. The correlations between the entangled photons were stronger than any local hidden variable theory would allow. Quantum mechanics was right. Einstein's dream of a locally real universe, a universe of particles carrying preset properties and no spooky action at a distance, was in trouble. Clauser's experiment was a landmark. It was the first time anyone had actually tested Bell's question in a laboratory, but the loopholes remained. The most significant one was called the detection loophole, or sometimes the fair sampling assumption. Because the detectors were not very efficient, they only caught a fraction of the photons that were emitted. Clauser and Friedman had to assume that the photons they did detect were a fair sample of all the photons that were produced. If that assumption was wrong, if the missed photons would have told a different story, then the violation of Bell's inequality might not be real. It was a reasonable assumption, but it was still an assumption. A truly definitive experiment would need to close that loophole. Another loophole was even subtler. It was called the locality loophole, or the communication loophole. In Clauser's experiment, the measurement settings on the two detectors were fixed in advance. They did not change during the experiment. That meant that, in principle, the detectors could have communicated with each other at the start, sharing information about what settings they would use. Or the particles themselves could have somehow known the settings in advance and adjusted their hidden variables accordingly. To close this loophole, you would need to change the measurement settings while the photons were already in flight, so fast that no signal, traveling at the speed of light, could possibly go from one detector to the other before the measurements were made. This required faster electronics and a new kind of experimental design. That design came from a French physicist named Alain Aspect. Aspect was a graduate student in the late 1970s, and like Clauser before him, he was captivated by Bell's question. He understood the loopholes in Clauser's experiment, and he set out to close them. In the early 1980s, working at the Institute of Optics in Orsay, near Paris, Aspect built an experiment that was a significant step forward. Aspect used a different source of entangled photons. Instead of an atomic cascade, he used a process called spontaneous parametric down conversion, in which a laser beam is shone through a special crystal and occasionally produces a pair of entangled photons. This source was brighter and more reliable than the one Clauser had used. But the real innovation was in the measurement settings. Aspect designed a system that could switch the polarization measurement angle very rapidly while the photons were in flight. He used a device called an acousto-optical switch, which could redirect the photons to different detectors based on a rapidly changing signal. The switching happened on a timescale of nanoseconds, billionths of a second. That was fast enough to ensure that no signal, traveling at the speed of light, could go from one detector to the other before both measurements were complete. The locality loophole, if not fully closed, was at least narrowed to a tiny crack. Aspect and his collaborators, Jean Dalibard and Gérard Roget, ran the experiment. They collected data, they counted coincidences, and the results were clear. Bell's inequality was violated. The correlations were exactly what quantum mechanics predicted. The hidden variable theories that obeyed locality were ruled out. The universe, at its deepest level, was not locally real. Einstein's spooky action at a distance, or something very much like it, seemed to be a fact of nature. Aspects experiments, published in 1981 and 1982, were a major milestone. They convinced many physicists who had been skeptical that Bell's question had been answered. But the loopholes were not completely closed. The detection loophole was still there, because the detectors still missed some photons, and there were other potential issues. Could there be some hidden communication between the detectors that was not blocked by the fast switching? Could the random number generators that chose the measurement settings be somehow correlated with the hidden variables of the photons? These were subtle questions, and answering them required even more careful experiments, stretching over decades. This is where Anton Zeilinger enters the story. Zeilinger is an Austrian physicist who has spent much of his career pushing the boundaries of entanglement experiments. In the 1990s and beyond, Zeilinger and his team at the University of Vienna, and later at the Institute for Quantum Optics and Quantum Information, conducted a series of experiments that closed more and more of the remaining loopholes. They used better sources of entangled photons. They used more efficient detectors. They separated the detectors by greater and greater distances, eventually sending entangled photons across kilometers of free space, between mountaintops and even up to satellites in orbit. One of the most significant experiments was done in 2015 by a collaboration of several groups, including Zeilinger's. This experiment closed both the detection loophole and the locality loophole simultaneously, for the first time. The researchers used a source of entangled photons that was efficient enough to catch a very high fraction of the pairs. They used fast random number generators to set the measurement angles while the photons were in flight, and they separated the detectors by a large enough distance, over a kilometer in some cases, to ensure that no light-speed signal could travel between them. The result was the same as before. Bell's inequality was violated. The correlations were quantum. The hidden variables were not there. There is a calmness to this story that is worth pausing on. It took more than 50 years, from Bell's paper in 1964 to the definitive loophole-free experiments of the 2010s, to fully answer the question. 50 years of patient work, 50 years of refining lasers and detectors and crystals and electronics, 50 years of quiet counting, of checking and rechecking, of closing one loophole after another. No one rushed. No one declared victory after the first experiment. The scientific process moved at its own steady pace, and the answer that emerged was all the more solid for the slow care with which it was obtained. In 2022, the Nobel Prize in Physics was awarded to John Clauser, Alain Aspect, and Anton Zeilinger, the three physicists who had done the most to turn Bell's question into a settled experimental fact. The Nobel Committee cited their work on entangled photons, their establishment of the violation of Bell inequalities, and their pioneering contributions to quantum information science. It was a recognition that had been a long time coming, and it was received with quiet satisfaction by a scientific community that had watched this story unfold over decades. So what exactly was settled? It is important to say this calmly and clearly. The experiments settled a specific question. They ruled out a particular class of theories, the local hidden variable theories that Einstein had hoped for. They showed that if hidden variables exist, they must be non-local. They must involve some kind of instantaneous connection between distant particles, a connection that cannot be explained by signals traveling through space. This does not mean that everything about quantum mechanics is settled. It does not mean that we understand what entanglement ultimately means. It does not tell us which interpretation of quantum mechanics is correct. Those questions are still open, still debated, still not knowing. We will sit with that not knowing in a later section. But the experimental result itself is settled. Bell's inequality is violated. The world is not locally real in the way Einstein envisioned. That is a fact, as well established as any fact in physics. Let us sit with that fact for a moment. It is a strange fact. It says that something we take for granted in everyday life, the idea that things are separate and that influences must travel between them, is not fundamental. It is an approximation, a useful rule for the big world, but it breaks down at the quantum scale. Two particles, once they have interacted, are not truly separate. They are parts of a single system, no matter how far apart they are. Measuring one is, in a very real sense, measuring the pair. The correlation between them is not caused by any signal. It is built into the structure of their shared existence. The experiments that demonstrated this were, in their physical details, quite beautiful in their simplicity. A laser beam, shining into a crystal. A pair of photons emerging, their polarizations linked, the photons traveling down optical fibers or through the open air. At each end, a detector, its measurement angle set by a random number generator. The detectors clicking, one by one, recording the arrival of individual photons. The data flowing into a computer, building up a statistical picture over many hours or days, and at the end, a number that exceeded the bound set by Bell's inequality, a number that said, quietly but firmly, the universe is not the way Einstein hoped it would be. There is no drama in this picture, just equipment on a table, just photons in the dark, just patient scientists checking their calibrations and drinking cups of tea while the data accumulated. Science at its most ordinary, which is also science at its most profound. The deepest questions about reality are not answered by thunderbolts. They are answered by careful measurements, repeated over and over, until the signal emerges from the noise and the pattern becomes unmistakable. And the pattern is now unmistakable. Entanglement is real. The correlations are non-local. The hidden variables, if they exist at all, must be stranger than even Einstein imagined. The spooky action is here to stay, not as a ghost story, not as a mystical force, but as a quiet, persistent feature of the physical world, built into the mathematics and confirmed by experiment. It is a fact you can rest with, a fact you can turn over in your mind, like a smooth stone found on a beach, feeling its weight and its strange shape, not needing to explain it, just letting it be what it is. As you lie here in the dark, you might think of those photons, still traveling. Clause's photons, Aspect's photons, Zeilinger's photons. They have long since been absorbed by detectors or scattered into the environment, but new photons are being entangled all the time, in laboratories around the world, in satellite links being tested for secure communication, in quantum computers being cooled to near absolute zero. The work continues, the questions continue, and the quiet answer, the same answer that has come back from every experiment for 50 years, continues to hold. The world is more connected than it appears. Separation is not the deepest truth. That is not a metaphor, it is a measurement. And it is a measurement you can carry with you into sleep, calm and steady, like the sound of distant waves. The world is more connected than it appears. Separation is not the deepest truth. That is a measurement, not a metaphor. And like all measurements, it has a precise meaning. It tells us something specific about how particles behave. But it is very easy, especially when we are drifting in the dark, to let the meaning stretch beyond what the science actually says. The imagination runs ahead of the facts. It spins stories, and those stories, however beautiful, are not always true. So now, calmly and carefully, we need to talk about what entanglement does not mean. We need to clear away some common misunderstandings, not as a correction, not as a scolding, but as a gentle tidying up, a way of making the room of our understanding a little more peaceful, a little more clear. The most common misunderstanding, the one that has spread farthest into popular culture, is the idea that entanglement can be used to send messages faster than light. The image is tempting. Two entangled particles, one here, one on the other side of the galaxy. You jiggle yours somehow, and the other one jiggles in response, instantly. You have a faster-than-light telegraph. You can send signals across the universe with no delay. This idea has fueled countless science fiction stories. It has become part of the folklore of quantum physics. And it is not true. Let us say this plainly. You cannot use entanglement to send a message. You cannot use it to communicate anything. You cannot use it to jiggle a distant particle in a way that carries information. The reason is simple, and it goes back to the nature of measurement in quantum mechanics. When you measure one particle of an entangled pair, you do not control the outcome. The outcome is random. Remember the blend of possibilities, the superposition. Before measurement, the particle is a cloud of maybe. When you measure it, the cloud collapses into one definite result. But which result you cannot choose. The universe chooses in a way that appears genuinely random. You might get spin up, you might get spin down. It is a 50-50 chance, and nothing you do can tip the odds. So you measure your particle, you get a result. It happens to be up. You now know, instantly, that if your distant friend measures their particle, they will get down. That is the correlation, that is the entanglement. But you did not send a message to your friend. You did not encode any information into the particle, because you could not control what the result would be. Your friend, when they measure their particle, gets down. They know, if they later compare notes with you, that you must have gotten up. But at the moment of measurement, all they see is a random result, down. It means nothing on its own. It is just a piece of data with no context. Only when you and your friend get together, or send ordinary signals by phone or radio or letter, and compare your results, does the pattern become clear. The pattern is real, the correlation is real, but the pattern can only be seen after the fact, using ordinary communication that obeys the speed limit of light. This is the crucial point. Entanglement is a correlation, not a communication channel. It is like two people on opposite sides of the world, each flipping a coin. Their coins are magically linked, so that whenever one comes up heads, the other comes up tails. But each person, on their own, just sees a random sequence of heads and tails. It is only when they compare notes later that they realize the sequences are perfectly anti-correlated. They cannot use their coins to send a message because they cannot control which face appears. The coins just flip randomly. The correlation is real, but the randomness prevents any information from being sent. This is not a technological limitation. It is not that we need better equipment or smarter scientists. It is a fundamental feature of quantum mechanics. The randomness of measurement outcomes is built into the theory, and every experiment to date has confirmed it. You cannot force an entangled particle to take a specific value. If you could, then entanglement would indeed allow faster-than-light communication, and that would violate the theory of relativity, which says that no signal can travel faster than light. But relativity is not threatened by entanglement. The two theories, quantum mechanics and special relativity, coexist peacefully because entanglement does not transmit any signal. It transmits only a correlation, and a correlation that can only be noticed after the fact. Another way to say this is that entanglement is not a force. It is not an interaction. It does not push or pull. When you measure your particle, nothing physically travels to the other particle. No energy moves, no momentum moves, no little flash of light. The other particle simply behaves, when measured, in a way that is consistent with the correlation that was established when the particles were created together. The measurement on one side does not cause the outcome on the other side, in the usual sense of cause and effect. It is more accurate to say that the two outcomes are jointly determined by the shared state of the pair. The pair is a single system, and measuring one part of it reveals information about the whole system. The information was not sent across the gap. It was already present, in the structure of the entangled state, from the moment the particles were created. This is a subtle point, and it is one of the places where even professional physicists can disagree about the right words to use. Some physicists prefer to say that there is no influence traveling between the particles at all. The correlation is simply a property of the joint system. Others prefer to say that there is a kind of non-local influence, but one that cannot be used to send signals. The difference between these views is, at some level, a matter of interpretation. What everyone agrees on is the experimental fact. No signal is sent, no message can be transmitted. The speed of light remains the ultimate speed limit for communication. Entanglement is strange, but it is not a loophole in the laws of physics. Another common misunderstanding is the idea that entanglement means that everything is connected to everything else, that there is a cosmic web of quantum links binding the whole universe together, that your thoughts are entangled with the stars, and that every action has instant consequences across the cosmos. This is a poetic idea. It has been embraced by many spiritual and philosophical traditions, and there is a grain of truth in it, in the sense that everything in the universe is ultimately made of the same quantum fields, and that particles have been interacting since the Big Bang. But the specific, testable phenomenon of entanglement is not a universal web. It is a fragile condition that must be carefully created and preserved. Entanglement is easily broken by interactions with the environment. That is the decoherence we touched on earlier. The air in the room, the warmth of your body, the ambient light, all of these things are constantly measuring quantum systems, collapsing their superpositions, breaking their entanglements. To create and maintain an entangled pair, you need careful isolation. You need vacuum chambers and cryogenic cooling and precise laser pulses. Entanglement is not the default state of the universe. It is a delicate, special condition that requires effort to produce. So when you hear that entanglement means all is one, you can smile and let the poetry be poetry. The science is more specific, and in its own way, more beautiful. It does not say that everything is entangled. It says that entanglement is possible. It is allowed by the laws of physics, and that possibility, that the universe permits two particles to be linked in this profound way, is enough. It tells us that separateness is not absolute. It tells us that the boundaries between things are not as hard as they appear. But it does not tell us that the universe is a single, conscious mind. Those are different stories, told in different languages, and they can coexist without one needing to be right and the other wrong. There is also a misunderstanding about what instant means in this context. When we say that the correlation between entangled particles is instant, we are being a little sloppy with language. What we mean is that, if you measure one particle and your friend measures the other at the same time, or what appears to be the same time in some frame of reference, the results will be correlated. But the concept of at the same time is tricky in relativity. Different observers, moving at different speeds, will disagree about which measurement happened first. This does not cause any paradoxes, because, as we have said, no signal is being sent. The correlation only becomes apparent when the two measurement results are brought together, and that bringing together must happen through ordinary means, at or below the speed of light. So the instantaneous aspect of entanglement is not a violation of relativity. It is a feature of the quantum description that has no classical analog, but it does not create causal conflicts. Let all of this settle for a moment. Entanglement cannot send messages. It cannot transfer energy. It cannot make your other particle jiggle on command. It is not a universal glue. It is not a psychic connection. It is a correlation, a very special kind of correlation, that exists between particles that have been prepared in a particular way. It is strange, yes. It is non-local, in the sense that the correlation cannot be explained by any local hidden variables, but it is also limited, constrained by the very rules that make it so puzzling. The randomness of measurement protects the speed of light. The fragility of entanglement limits its reach. The universe, in its wisdom, has given us something strange, but it has not given us a way to break its own deepest laws. Why does this misunderstanding persist? Because the idea of faster-than-light communication is exciting. It captures the imagination. It suggests a way around the vast, lonely distances of space. And because the phrase, spooky action at a distance, which Einstein coined as a criticism, has been taken up as a kind of advertising slogan. It sounds magical. It sounds like something out of a fairy tale. And so the popular imagination has run with it, building a picture of entanglement that is more fiction than fact. There is no harm in this, as long as we are clear about what is fiction and what is fact. The fiction is a story. The fact is also a story, but a quieter one, a more careful one, and it has its own beauty. The beauty of a correlation that is stronger than any classical correlation could be. The beauty of a connection that is not a signal, not a force, not a message, but something else entirely. Something for which our language does not yet have a perfect word. If you have ever been confused about this, if you have ever wondered why we cannot build an Ansible, a faster-than-light communicator, using entangled particles, know that you are in good company. The confusion is natural. It comes from the same place as Einstein's discomfort. Our minds are built for a world of separate objects and definite properties and signals that travel through space. When we encounter something that does not fit those categories, we try to force it into one of them. We think, if the correlation is instant, it must be a signal. But it is not a signal. It is a different kind of thing. Learning to accept that different kind of thing, without trying to force it into a familiar box, is one of the quiet pleasures of studying quantum physics. It stretches the mind. It loosens the grip of old assumptions. And that stretching, that loosening, can be very restful. So as you lie here, let go of the idea that entanglement is a communication channel. Let go of the idea that it is a universal web. Let go of the idea that it breaks the speed of light. Those are all stories we tell because we want the universe to be more like a human story. But the real universe is stranger and calmer than that. It does not need to communicate. It just is. Two particles, linked, holding their correlation across the dark, not sending anything, not receiving anything, just being what they are. And that is enough. That is more than enough. It is a fact you can hold in your mind without needing it to do anything for you. A quiet fact, like the fact of gravity or the fact of starlight. It simply is, and you can simply rest, knowing that you do not need to understand everything tonight. Even the parts you do not fully grasp can be companions in the dark. They can sit with you, quietly, not asking for attention, just being there, like the faint glow of a distant star. We have cleared away some of the misunderstandings. We have said what entanglement does not do. It does not send messages. It does not break the speed of light. It is not a universal web connecting all things. It is a specific, testable, fragile correlation between particles that have been prepared in a special way. That is the fact. The measurement. The thing that experiment after experiment has confirmed. But then we are left with a question. A quiet, lingering question. What does it mean? Not what does the mathematics predict, not what do the detectors count, but what does it say about the nature of reality itself? This is where the calm not knowing really opens up. Because the experiments have settled the specific question that Bell asked, local hidden variables of the kind Einstein hoped for are ruled out, but the experiments have not settled the deeper question of what quantum mechanics is telling us about the world. There are several different ways of interpreting the same experimental results, and none of them has been proven right or wrong. Physicists live with this. They have learned to hold the different interpretations lightly, as possibilities, as ways of thinking, without needing to pick a winner. And we can do the same. We can let this open-endedness be part of the calm. Let us start with the oldest and most widely taught interpretation. It is called the Copenhagen interpretation because it was developed largely by Niels Bohr and his colleagues at his institute in Copenhagen in the 1920s. The Copenhagen interpretation says, in plain terms, that quantum mechanics is a tool for calculating the probabilities of measurement outcomes, and that it does not describe an objective reality independent of measurement. Before measurement, the particle is not in any definite state. It is in a superposition, a cloud of possibilities. The wave function is not a physical thing, it is a mathematical tool for making predictions. When a measurement happens, the wave function collapses, and a definite outcome appears. What causes the collapse? The Copenhagen interpretation does not say, exactly. It treats measurement as a fundamental process that cannot be reduced to anything simpler. the observer, the measuring device, and the quantum system are all part of a single, indivisible phenomenon. Reality is what happens when you look. Before that, it is not just unknown. It is genuinely indefinite. This is a very pragmatic view. It says, in essence, stop asking what is really there before you measure. The theory works. Use it. Do not worry about what the world is like when you are not looking. For many working physicists, this is enough. They do not need to settle the philosophical questions. They have experiments to run, calculations to do, technologies to build. The Copenhagen interpretation gives them a framework that works, and they are content to leave the deeper questions for another day. But not everyone is content with that. Some physicists and many philosophers feel that the Copenhagen interpretation leaves something out. It draws a line between the quantum world and the classical world, between the system being measured and the measuring device. But it does not say exactly where that line is. Does the wave function collapse when a photon hits a detector? When the signal is amplified? When a human looks at the readout? The Copenhagen interpretation does not specify. It treats the classical world of measurement devices as given, but in principle, those devices are also made of quantum particles. So why do they not also exist in superpositions? This is the measurement problem, and it remains unsolved. Another interpretation, which has gained popularity in recent decades, takes a very different approach. It is called the many worlds interpretation, and it was first proposed by a physicist named Hugh Everett in the 1950s. The many worlds interpretation says that the wave function does not collapse, not ever. Instead, when a measurement happens, the universe branches. All possible outcomes happen, each in a separate branch. If a particle is in a superposition of spin up and spin down, and you measure it, the universe splits into two branches. In one branch, you see spin up. In the other branch, another version of you sees spin down. Both branches are equally real. They just do not interact with each other. The branching happens constantly, everywhere, at every moment, across the entire cosmos. The universe is like a tree that never stops growing new limbs. In plain terms, the many worlds interpretation says that there are many, many parallel realities, all coexisting, all equally real, and that quantum mechanics is a theory of this branching structure. There is no special role for measurement. There is no collapse. There is just the smooth, continuous evolution of the universal wave function, which contains all possible histories and all possible futures. We only see one branch because we are part of the branch. Our conscious experience follows one path through the branching tree. The many worlds interpretation is elegant in its own way. It removes the need for a mysterious collapse process. It treats the whole universe as a quantum system, with no arbitrary dividing line between quantum and classical. But it comes at a cost. The cost is the existence of an enormous, perhaps infinite, number of parallel worlds that we can never observe. Some physicists find this cost too high. Others find it acceptable, even beautiful. The debate continues, and no experiment has settled it. A third interpretation, less widely held but still actively studied, is called pilot wave theory, or de Broglie-Bohm theory, after the physicists who developed it, Louis de Broglie and David Bohm. Pilot wave theory says that particles do have definite positions at all times, even when we are not looking. There are no superpositions in the fundamental ontology. The particle is always somewhere specific, but the particle is guided by a wave, the wave function, which evolves according to the Schrödinger equation. The wave acts as a kind of invisible pilot, steering the particle along its path. The wave is real, but it is not made of ordinary matter. It is a new kind of physical entity, a field that exists everywhere and determines how particles move. In pilot wave theory, entanglement is explained through the action of the pilot wave. When two particles are entangled, their pilot waves are linked, and a measurement on one particle instantly affects the pilot wave of the other, which in turn affects the motion of the other particle. This influence is faster than light, so pilot wave theory is explicitly non-local. It gives up locality. the idea that distant things cannot influence each other instantly. But it keeps determinism and realism. Particles have definite properties. The future is fully determined by the past. The randomness of measurement outcomes is due to our ignorance of the exact initial conditions, not to any fundamental indeterminism. Pilot wave theory makes the same predictions as standard quantum mechanics for all known experiments, so it cannot be ruled out by any data we currently have. It is a consistent, deterministic alternative. But it is less widely accepted, partly because the non-locality is hard to reconcile with relativity, and partly because it requires introducing this new, invisible pilot wave that acts on particles, but is not directly detectable. Still, it has its advocates, and it remains a live option in the ongoing debate. There are other interpretations too. Quantum Bayesianism, or QB-ism, treats the wave function as a representation of an observer's subjective beliefs, not as a physical object. Objective collapse theories modify the Schrödinger equation so that superpositions spontaneously collapse when they get too big, without the need for a measurement. Each interpretation has its strengths and its weaknesses. Each tries in its own way to make sense of the same experimental facts, and none has been proven correct. This is the not knowing that sits at the heart of quantum mechanics. It is not a gap we can rush past. It is not a loose end that will be tied up any day now. It is a deep, structural feature of the theory. Quantum mechanics works. It makes predictions of extraordinary accuracy, but what those predictions mean for the nature of reality is still an open question, and that is fine. That is part of the calm. Physicists have learned to live with this not knowing. They use the theory, they refine the experiments, they build the technologies, and they let the philosophical questions sit, unresolved, waiting for new insights or new experiments that might, someday, narrow the field of possibilities. Think of it like this. Imagine you have a map that perfectly predicts the weather. You can tell, with great accuracy, whether it will rain tomorrow, what the temperature will be, how strong the wind will blow. The map works. Every sailor, every farmer, every pilot relies on it. But no one knows exactly how the map works. Is it a description of real, deterministic processes in the atmosphere? Is it a statistical summary of inherently random events? Is it a reflection of our limited knowledge, or of an objective indeterminism? Different people have different views. The map works regardless, and the rain still falls regardless. Quantum mechanics is like that map. It works. It works with stunning precision. But what it is a map of, what the territory really looks like, is something we are still figuring out. Sitting with this not knowing can be very restful. It loosens the grip of the need for certainty. It invites a kind of intellectual humility. The universe is not obligated to make sense to us. It is not obligated to fit into the categories our brains evolved to handle. It is what it is, and we are slowly, patiently, learning to describe it. The descriptions we have are good. They are useful. They are true in the sense that they match the data. But they may not be the final story. There may be a deeper story, one that we have not yet found the words for. Or there may not. The world may simply be probabilistic at its foundations, with no deeper layer of deterministic machinery. We do not know, and that is fine. As you lie here in the dark, you might feel a kinship with the physicists who wrestle with these questions. They are not anxious about the not knowing. They are curious. They are patient. They have work to do, and they do it, and they let the mystery be a companion rather than a problem. You can do the same. You do not need to pick an interpretation. You do not need to decide whether Copenhagen or many worlds or pilot wave is the right one. You can just let them all sit there, like different paintings of the same landscape, each capturing something true, none capturing everything. The landscape itself is still there, in the dark, waiting for the next morning, when the light will fall on it from a slightly different angle and reveal something new. The story of entanglement does not end with a neat conclusion. It ends with an open door. A door onto a landscape of possibilities, And that is where we are going next, from the philosophical to the practical, from the not knowing to the doing. Because even while the debates about meaning continue, physicists and engineers have been building things with entanglement, real things, useful things, things that are already changing the way we handle information, keep secrets, and compute the uncomputable. That is a different kind of wonder, a quieter kind, the wonder of taking something deeply strange and making it work for us. And that is where we will drift next. Not with urgency, not with hype, just with the slow, steady recognition that the universe, in all its strangeness, is also generous. It gives us connections we did not expect, and it lets us use them, even when we do not fully understand what they mean. We have traveled a long way. From the world of the very small, through superposition and entanglement, through Einstein's discomfort and Bell's quiet question, through the patient experiments that confirmed the strangeness, and through the open questions of what it all might mean, we have sat with the not knowing. We have let it be calm. Now we turn a corner, into the practical, into the realm of doing, because entanglement is not just a puzzle to be pondered. It is also a tool, a resource, something that can be used to build things that were not possible before, and people have been building. Quietly, steadily, over decades, they have been turning the strange correlations of quantum particles into real technologies. This is not science fiction, it is engineering, built on the settled science we have been exploring. The first technology we will talk about is called quantum cryptography. The word cryptography means secret writing, the art of sending messages that cannot be read by anyone other than the intended recipient. For centuries, people have devised codes and ciphers, ways of scrambling messages so that even if they are intercepted, they remain unreadable. But every code, in principle, can be broken. The security of a code depends on the difficulty of a mathematical problem. If someone builds a computer fast enough or discovers a clever enough mathematical trick, the code can be cracked. There is one exception, a method that is not vulnerable to any amount of computing power or mathematical cleverness. It is called the one-time pad, and it requires the sender and receiver to share a secret key, a string of random numbers, that is as long as the message itself. If the key is truly random and is used only once, the encryption is unbreakable. The problem, for most of history, has been how to share the key. If you have a secure way to share the key, you could just use that secure way to share the message. The key distribution problem has been the bottleneck. Quantum cryptography solves the key distribution problem using entanglement. The idea, in plain terms, is this. You create a stream of entangled pairs of photons. You send one photon from each pair to one location, and the other photon to another location. The two parties, usually called Alice and Bob in the literature, measure their photons. Because the photons are entangled, their measurement results are correlated. Alice and Bob can then compare a small portion of their results over a public channel, like a phone line or the internet. By checking whether the correlations match what quantum mechanics predicts, they can detect if anyone has been eavesdropping. If an eavesdropper, usually called Eve, tries to intercept and measure the photons, she will disturb the entanglement. Her measurement will act like any measurement in quantum mechanics. It will collapse the superposition and break the delicate correlations. Alice and Bob will see that something is wrong. They will know the channel is not secure, and they will not use that key. If the correlations are perfect, they know no one has been listening, and they can use the remaining measurement results to build a secret key. That key can then be used with a one-time pad to encrypt a message with absolute security. This is not just theory. Quantum key distribution, as it is formally called, has been demonstrated in laboratories for decades. It has been tested over fiber optic cables stretching tens of kilometers. It has been demonstrated between ground stations and satellites in orbit. There are companies that sell quantum cryptography systems. Banks and governments have used them. The technology is real, it works, and it is based directly on the principles of entanglement and superposition that we have been talking about. The security comes not from the difficulty of a mathematical problem, but from the fundamental laws of physics. You cannot measure a quantum system without disturbing it. That is not a technological limitation, it is a law of nature, and that law can be harnessed to detect eavesdropping with absolute certainty. There is a calm elegance to this. The very thing that made Einstein uncomfortable, the idea that measurement disturbs reality in some fundamental way, becomes a feature, not a bug. It becomes a shield. The fragility of quantum states, which makes them so hard to study, makes them perfect for detecting intruders. A quantum message carries its own tamper-evident seal. If you touch it, you leave a mark, and that mark is detectable, no matter how careful you are. The second technology is called quantum teleportation. The name is unfortunate because it suggests something out of science fiction. It sounds like beaming people from starships to planets. It is not that. Quantum teleportation is a way of transferring the exact quantum state of one particle to another particle, far away, without moving the first particle through the space between. It does not move matter. It does not move energy in the usual sense. It moves information, quantum information, in a way that is made possible by entanglement. Let us describe it slowly. Suppose you have a particle, call it particle A, in some unknown quantum state. You want to send that exact state to a distant location. You cannot just measure the state and send a classical message describing it, because measurement disturbs the state. You would only get a random outcome, and you would not capture the full quantum information. And you cannot copy the state, because quantum mechanics forbids copying. This is called the no-cloning theorem, and it is another fundamental law. A quantum state is unique. It cannot be duplicated, but you can teleport it. To do this, you first need an entangled pair of particles, call them B and C, shared between the sender and the receiver. The sender has particle A and particle B. The receiver has particle C. The sender performs a special kind of joint measurement on A and B, called a Bell state measurement. This measurement entangles A and B in a way that also affects C, through the pre-existing entanglement between B and C. The sender gets one of 4 possible random outcomes. They send those 2 bits of classical information, just an ordinary 2-bit number, to the receiver over an ordinary channel. Depending on which outcome the sender got, the receiver applies a specific operation to particle C, and after that operation, particle C ends up in the exact same quantum state that particle A was in originally. The state has been transferred, teleported. Notice what happened. The original particle A was measured, and its state was destroyed. The information was not copied, it was moved. The entangled pair B and C acted as a kind of bridge, a channel for quantum information. And the classical message, the 2 bits, was essential. Without those 2 bits, the receiver cannot reconstruct the state. This means that quantum teleportation does not allow faster-than-light communication, because the classical message travels at or below the speed of light. The rules of relativity are respected. Quantum teleportation has been demonstrated in laboratories many times. It was first done with photons in the 1990s. It has since been done with atoms, with ions, with more complex systems. It is a core technique in quantum information science. It is not a way to move people or objects. It is a way to move the delicate, fragile state of a quantum system from one place to another. And it is a necessary building block for quantum networks, for quantum repeaters that can extend the range of quantum communication, and for distributed quantum computing. The third technology is perhaps the most widely discussed, though it is still in its early stages. It is the quantum computer. A quantum computer is a machine that uses superposition and entanglement to process information in ways that ordinary, classical computers cannot. An ordinary computer stores information in bits. Each bit is a 0 or a 1. A quantum computer stores information in quantum bits, or qubits. A qubit can be in a superposition of 0 and 1, and multiple qubits can be entangled. This gives quantum computers a different kind of power. They can explore many possibilities at once, in a sense, by operating on superpositions of all the possible inputs at the same time. This does not mean quantum computers are just faster versions of ordinary computers. They are not better at everything. For many problems, a classical computer is just as good. But for certain specific problems, quantum computers offer a different way of attacking the problem, a way that can be exponentially more efficient. The most famous example is factoring large numbers. The security of much of the internet relies on the fact that it is very hard, with a classical computer, to find the prime factors of a large number. A quantum computer, running an algorithm devised by the mathematician Peter Shor in 1994, could do it much faster. This is one of the reasons quantum cryptography is being developed. We need new forms of security that are not vulnerable to quantum factoring. Other problems that quantum computers might help with include simulating molecules and chemical reactions, which are themselves quantum systems. A quantum computer could, in principle, simulate a molecule directly by using qubits to represent the electrons and their interactions. This could lead to new drugs, new materials, new catalysts. There is also the possibility of speeding up certain kinds of optimization problems or machine learning tasks. But the field is still young. The quantum computers that exist today are small. They have a few dozen qubits, or a few hundred depending on the technology. They are noisy. They make errors. They are not yet doing useful work that a classical computer cannot do faster. But they are improving, slowly and steadily, year by year. Companies like Google, IBM, and others have built prototype quantum processors. Research groups around the world are working on better qubits, better error correction, better algorithms. What is important for our purposes tonight is not the details of the technology. It is the simple fact that these machines rely on superposition and entanglement. Those strange, counterintuitive properties that we have been sitting with in the dark are not just philosophical curiosities, they are resources. They can be harnessed to do computation. A qubit in a superposition of 0 and 1 is not just a vague maybe. It is a computational asset. Two qubits that are entangled are not just a spooky mystery, they are a logic gate waiting to happen. This is a quiet kind of wonder. The universe, at its most fundamental level, works in a way that is deeply strange to our everyday intuition. And yet that strangeness is not sealed off from us. It is accessible. We can reach down into the quantum world and shape it, nudge it, use it. We can build machines that speak the native language of reality. And we are doing this not by fully understanding what it all means, but by understanding the rules well enough to follow them. The mathematics works, the experiments confirm the mathematics, and the engineering follows the experiments. This is also a reminder that the science we have been talking about is settled. It is not speculative. It is not controversial. The technologies of quantum cryptography, quantum teleportation, and quantum computing are built on the same principles that were debated by Einstein and Bohr and tested by Clauser and Aspect and Zeilinger. Those principles have been verified to an extraordinary degree of precision. The technologies work because the science is correct. The spooky action is real. The superposition is real. The entanglement is real. And we are learning to use them. As you lie here, you might think about the quiet hum of a quantum computer in a laboratory somewhere. It is probably in a basement, shielded from vibrations and electromagnetic noise, cooled to a temperature colder than outer space. Inside, a tiny chip holds a handful of qubits, each one a small superconducting circuit or a trapped ion. The qubits are in superpositions. They are entangled with each other. Pulses of microwave radiation or laser light nudge them through a sequence of operations. And at the end, a measurement is made, and a result is read out. The whole process is delicate. It requires extraordinary control. But it works. It is a triumph of patience and precision. And you might think about the photons flying through fiber optic cables, carrying entangled states from one end of a city to another, forming the backbone of a quantum network. or the photons beaming down from a satellite, having been entangled on board and sent to two different ground stations, proving that entanglement survives the journey through the atmosphere. These are not dreams, they are demonstrations that have already happened. The quantum internet, if it comes to pass, will be built on the principles we have been discussing. None of this requires us to solve the measurement problem. None of this requires us to choose between Copenhagen and many worlds and pilot wave. The engineering works regardless. The universe gives us its correlations, and we use them, even while the deeper meaning remains open. That is a very calming thought. It suggests that we do not need to have everything figured out to make progress. We can work with what we know and let the mysteries remain mysteries, and still build beautiful things. So let your mind rest on that for a while. The strange connection between tiny particles is not just a story for late nights. It is a fact of the world, a fact that is slowly being woven into the fabric of our technology. The same entanglement that troubled Einstein is now protecting bank transfers and simulating molecules. The same superposition that Schrödinger found so puzzling is now powering new kinds of computation. The world of the very small, which seemed so remote when we first descended into it, is turning out to be useful, not in a way that diminishes its strangeness. The strangeness remains, but it is a strangeness we can hold and shape and put to work. And that is a quiet kind of beautiful. The universe is strange, and we are part of the universe, and we are learning to speak its language, one photon, one qubit, one entangled pair at a time. We are learning to speak the language of the universe, one photon, one qubit, one entangled pair at a time. That is a quiet and beautiful thought. And now, as we begin to wind down, as the night settles more deeply around us, it is time to widen the lens, to step back from the details of superposition and Bell's inequalities and quantum cryptography, and to look at the bigger picture. What does all of this tell us about the nature of the universe? What does it say about the world we live in, the world we are part of, the world that made us? The first thing to say, calmly and plainly, is that the universe at its smallest scale behaves differently than the world we see and touch. This has been the refrain throughout our journey. Atoms are not little marbles, electrons are not tiny baseballs, photons are not bullets of light. The rules of the very small are not the rules of the very big. And that in itself is a profound fact. It means that reality is layered. The surface layer, the layer of tables and chairs and cups of tea, is governed by one set of rules, the rules of classical physics. But underneath that layer, at the level of the particles that make up everything, a different set of rules applies, the rules of quantum physics. And those rules are not just a small correction to the classical rules. They are fundamentally different. They involve superpositions and entanglements and probabilities that are not merely ignorance, but seem to be woven into the fabric of things. This layering is not a contradiction. It is a harmony. The quantum rules, when applied to large collections of particles, give rise to the classical rules we know. The strangeness does not disappear. It is still there, in every atom, in every molecule. But it averages out. It becomes hidden by the sheer complexity of the big world. A single electron can be in a superposition of here and there. A baseball cannot. Or rather, the baseball is in a superposition technically, but the superposition is so fragile, so easily washed away by decoherence, that it vanishes in an instant, far too fast to ever be noticed. The classical world emerges from the quantum world, like a smooth image emerging from a mosaic of tiny, discrete tiles. The smoothness is real, but so are the tiles. This is one of the great intellectual achievements of the 20th century. The realization that the solid, dependable, cause and effect world we experience is built on a foundation that is none of those things. The foundation is probabilistic, not deterministic. It is interconnected in ways that violate our everyday notions of locality. It is indefinite until measured. And yet, it gives rise to the definite, local, deterministic world we know. How exactly that happens, the precise boundary between the quantum and the classical, is still a subject of study and debate. The measurement problem, which we touched on in the section on interpretations, is still open. But the fact that it does happen is not in doubt. We are here. We are made of quantum particles. And we are, undeniably, definite. The transition from quantum to classical is a fact of nature, even if we do not fully understand every step of it. The second thing to say is that entanglement challenges the intuition that separate things must be truly separate. This is perhaps the deepest shift in perspective that quantum mechanics asks of us. In our everyday lives, we take separateness for granted. You are you. The bed is the bed. The air is the air. The stars are the stars. Everything has its own location, its own properties, its own independent existence. That is the common sense view, and it works for almost everything we do. But entanglement tells us that this common sense view is not fundamental, it is an approximation. It works at our scale, for reasons we understand, but it breaks down at the smallest scales. Two particles that have interacted can remain connected in a way that makes them, in a very precise sense, not separate. They are parts of a single quantum system, even when they are far apart. Measuring one is also, in a sense, measuring the pair. The correlation between them is not caused by any signal traveling through space. It is built into the structure of their shared state. The whole is more fundamental than the parts. This is not a metaphor. It is a mathematical and experimental fact. But it is very hard to resist drawing larger implications from it. If separateness is not fundamental at the quantum scale, what does that say about the separateness we experience at the human scale? Is it also an approximation? Is it also a kind of useful illusion, a surface phenomenon that hides a deeper interconnectedness? The science does not answer these questions. It cannot. They are philosophical, even spiritual questions. But the science does give us a new image to think with, an image of a universe where connection is as fundamental as separation, where the boundaries between things are softer than they appear, where the very idea of thing might need to be rethought. You do not need to draw any conclusions from this. You do not need to build a worldview on it, but you can let it sit with you, in the dark, as a quiet possibility. The possibility that the loneliness of separate existence is not the whole story, that underneath the surface, at the deepest level, the universe is more like a web than a collection of isolated fragments. This is a thought that many people, in many traditions, have arrived at through contemplation or intuition or faith. Quantum physics does not prove those traditions right, but it does offer a kind of resonance, a scientific echo of an ancient intuition, and that resonance, that quiet harmony between the very old and the very new, can be a restful thing to fall asleep to. The third thing to say is that quantum mechanics, despite all its strangeness, is one of the most thoroughly tested theories in the history of science. This is worth repeating, because the strangeness can sometimes make it feel like speculation. It is not. The predictions of quantum electrodynamics, the theory of how light and matter interact, have been tested to parts in a trillion. The predictions of entanglement experiments have been confirmed in laboratory after laboratory, with ever greater precision, for over 50 years. The technologies built on quantum mechanics, from the transistor to the laser to the quantum computer, work. They work every day, in millions of devices, all over the world. The theory is not in doubt. The theory is correct. What is still open is what the theory means. We have spent time with that openness. The Copenhagen interpretation, the many worlds interpretation, pilot wave theory, and others. They all agree on the experimental predictions. They all disagree on what those predictions say about the nature of reality. And that disagreement is not a weakness. It is a sign of intellectual health. It means that physicists are still thinking, still questioning, still not satisfied with easy answers. The not knowing is not a failure. It is an invitation. An invitation to keep looking, keep probing, keep asking. And for those of us who are not physicists, it is an invitation to humility. To the recognition that even the experts, the people who have spent their lives studying this, do not have the final answers, and that is fine. That is more than fine. It is a reminder that the universe is larger and stranger than any single human understanding. It can hold all our interpretations, and more, without being diminished. So here we are, near the end of our journey. We have gone from the world of the very small to the strange blend of superposition, to the linked fates of entangled particles, to Einstein's discomfort and Bell's quiet question, to the patient experiments that confirm the strangeness, to the technologies that are beginning to harness it. And now we are stepping back, looking at the whole landscape. It is a landscape of proven facts and open questions, of precise mathematics and unresolved philosophy, of deep strangeness and practical utility. It is, in short, a landscape very much like the rest of human knowledge. We know some things, we do not know others. The boundary between the known and the unknown is always shifting, and there is always more to learn. But tonight is not for learning more. Tonight is for resting with what we have, for letting the ideas settle softly, like snow on a quiet field. You do not need to solve the measurement problem. You do not need to pick an interpretation. You do not need to understand every detail of Bell's inequality or quantum teleportation. You can just let the broad outlines of the story stay with you. The universe is not built the way we thought. It is stranger, and more connected, and more beautiful. And that is a thought you can carry with you into sleep. Some mysteries can be lived with. They can be studied slowly, over lifetimes, over generations, without needing to be solved tonight. The mystery of entanglement is one of those. It has been unfolding for almost a century, and it is still unfolding. Every few years, a new experiment tightens a loophole. Every so often, a new interpretation is proposed, or an old one is revived. The conversation continues, the questions remain open, and that ongoing conversation, that patient, collective inquiry, is one of the most beautiful things about being human. We can sit with mystery, we can be puzzled and not panic. We can be uncertain and still be calm. As you lie here, let that calm settle over you, the calm of not knowing everything, the calm of being part of a universe that is still, in many ways, a frontier. The calm of knowing that the same particles that make up your body are governed by the same strange rules we have been exploring. You are not separate from the mystery. You are made of it. Every electron in your atoms is a cloud of possibilities. Every photon that enters your eyes carries the legacy of entanglement. You are a quantum system, even if you do not feel like one, and that is not a problem to be solved. It is a fact to be rested with. The bigger picture, in the end, is not a picture at all. It is a window onto a landscape that extends far beyond the frame. We have been looking through that window together, in the quiet dark, and we have seen some strange and beautiful things. But the window is still open, the landscape is still there, waiting for another night, another conversation, another slow drift toward understanding. For now, it is enough to know that the window is there, and that you can always come back to it whenever you like and look out again. The universe will still be there, strange and connected and calm, and you will still be part of it. Never separate, never alone, just a quiet part of a quiet whole, drifting in the dark. Just a quiet part of a quiet whole, drifting in the dark. That is where we find ourselves now, at the end of our journey, at the close of the story. But there is no real ending, just as there was no real beginning. The particles we have been talking about have been here since the start of the universe. The entanglements we have been tracing have been woven into the fabric of things for billions of years. We just stopped, for a little while, to notice them. And now, as the night settles deeper around you, we can let them go. We can let the words fall away and let the quiet take over. Two particles. That is the core image. The thing we have been circling around from the very beginning. Two particles, created together, linked in a way that their properties stay connected. They move apart. They travel across a room, across a city, across the space between the stars. And yet, they are still connected. Measuring one tells you about the other, not because a signal traveled between them, not because they sent a message across the gap, but because they were never truly separate to begin with. They are two parts of a single quantum system. The whole came first. The parts are just ways that the whole shows up when we look. That image, held softly in the mind, is enough. It does not need to be explained further. It does not need to be turned into a lesson or a moral. It is just a fact about the universe. A fact that has been tested and confirmed and settled over decades of patient work. And it is a fact you can rest with. A fact you can let sit beside you in the dark, not demanding anything, not asking to be understood, just being what it is. We have traveled a long way together. We started with the world of the very small, that hidden landscape inside every atom, where electrons and photons live. We learned that at that tiny scale, particles do not behave like marbles or baseballs. They are more like clouds of possibility, more like hazes of maybe. We learned that this strangeness is called quantum physics, and that it is not a fringe idea. It is one of the most thoroughly tested theories in the history of science. We learned about superposition, the idea that a single particle can be in a blend of possible states until it is measured. A coin that is both heads and tails until you look. Not because you do not know which side is up, but because the coin itself has not decided. That is a strange idea, and we let it be strange. We did not try to force it into an everyday box. We just let it sit there, a quiet wonder at the heart of things. Then we learned about entanglement. Two particles, sharing that superposition. Their possibilities linked, so that the state of one is tied to the state of the other. Measure one, and you instantly know about the other, no matter the distance. Not a message, not a signal, just a correlation built into the structure of their shared existence. Schrödinger gave this state its name in 1935, and it has been puzzling and delighting physicists ever since. Einstein found it deeply troubling. He called it spooky action at a distance, and he spent years trying to find a way around it. He believed that the particles must carry hidden properties, preset from birth, that explained the correlations without any need for spookiness. He was not wrong to ask the question. His discomfort was a gift. It sharpened the debate. It led, eventually, to the experiments that settled the matter. John Bell, in the quiet of the 1960s, found a way to ask nature herself whether Einstein's hidden variables could explain entanglement. He derived a mathematical bound, an inequality, that local hidden variables would have to obey. Quantum mechanics predicted that the bound would be broken, and when the experiments were finally done, by Clauser and Aspect and Zeilinger and others, they found that the bound was indeed broken. The universe is not locally real, in the way Einstein hoped. The correlations are real. The entanglement is real. The spookiness, whatever it means, is here to stay. We took care, after that, to say what entanglement does not mean. It does not mean we can send messages faster than light. It does not mean that everything is entangled with everything else. It does not mean that the universe is a cosmic mind. It is a specific, testable, fragile phenomenon, and it is beautiful in its specificity. The limits are part of the beauty. The randomness of measurement protects the speed of light. The fragility of entanglement explains why we do not see it in our everyday lives. The world is strange, but it is not lawless. It follows rules, and the rules are consistent, even when they are unfamiliar. We sat with the open questions. What does entanglement mean for the nature of reality? The experiments are settled, but the interpretations are not. Some physicists think that the wave function collapses when a measurement is made. Some think that the universe splits into many branches, each containing one possible outcome. Some think that particles are guided by invisible pilot waves. All of these views are consistent with the data. None has been proven correct, and that not knowing is not a problem to be solved. It is a space to rest in, a quiet open field where the questions can live without needing to be answered tonight. We looked at what entanglement is used for. Quantum cryptography, which uses entangled photons to create codes that cannot be intercepted without leaving a trace. Quantum teleportation, which transfers the state of a particle across a distance, using entanglement as a bridge. Quantum computers, which use superposition and entanglement to process information in new ways. These are real technologies, built on decades of settled science. They are not magic, they are engineering, and they remind us that even the strangest features of the universe can be put to work, gently, patiently, without needing to fully understand what they mean. Then we widened the lens. We saw that the universe, at its smallest scale, is different from the world we touch. That separateness is not fundamental, that connection is woven into the fabric of things, and we let that thought settle, not as a conclusion, but as a companion, a quiet thought to carry with us into the night. And now we are here, at the very end. The words are slowing down, the sentences are getting shorter, the pauses are getting longer. This is the time for letting go, for letting the ideas drift away, like leaves on a slow river. You do not need to hold on to any of it. You do not need to remember the names or the dates or the terms. If something stays with you, let it stay. If nothing stays, that is fine too. The purpose was never to teach you something. The purpose was to give you something to rest your mind on, a gentle focus that asked nothing in return. And now that focus can dissolve. Think one last time of those two particles. They were created together, in some distant past, in some quiet corner of the universe. They have been traveling ever since, in opposite directions, across the vast dark spaces between the stars. They are far apart now, farther than any distance you can imagine, and yet they are still connected, still one thing, still holding their shared secret. They do not send signals to each other, they do not need to. The connection is not something they maintain, it is something they are. That is the image to hold as you slip away. Two particles, linked since their creation, still connected across distance. A quiet reminder that separation is not the deepest truth. That the universe, at its foundations, is more unified than it appears. That you, lying here in the dark, are not an isolated point. You are part of the web. You are made of the same particles, governed by the same rules, born from the same ancient stars. The boundaries between you and the world are softer than they seem. The darkness around you is not empty. It is full of connections older than measurement, older than time, older than the first light. Not understanding everything is fine. Even physicists sit with the mystery. They go to bed at night, like you, with questions still open, with puzzles still unsolved. The universe does not demand that we figure it out. It just is, and we are part of it, and that is enough. Quiet space. Distant light. Connections older than measurement. Two particles, still linked, still one thing, still holding their quiet secret across the endless dark. Let that be the last thought, or let there be no thought at all. Just the slow rhythm of your breath, just the weight of your body on the bed. Just the quiet dark holding you gently, the way the universe holds its particles, never truly separate, never truly alone. Rest now, the story is done. There is nothing more to follow, nothing more to understand, just the stillness, just the night, just you, drifting in the quiet, connected to everything, and perfectly, peacefully at rest.